and listen to all these great Capstone presentations. I know that all teams worked really hard this year. Yeah, thank you all. So let's get into it. Cool. I'm Keegan.
I'm Danny.
I'm Noah.
I'm Jesus.
And I'm Marco. All right, so what is Project Dragonfly? So typically with drone flights, you need a ton of different sensors. You need something to measure altitude, magnetic field, list just goes on and on. It's a bunch of sensors. So what Project Dragonfly does is we get all these sensors, and rather than dealing with the headache of dealing with them one at a time, we put it into one single peripheral device, and we have it as sort of a plug-and-play device where you can just attach it via USB to any drone, and this will allow you to provide state estimation. And also one of our goals is to keep our device as small as possible. So as I mentioned earlier, in doing so, we hope to make it much more cost-effective, modular, and just reduce the headache that comes with drone flight and multi-sensor configuration involved.
So let's break down kind of our main project domains we have. We have our hardware, our firmware, and our software. So we're going to start it off. We're going to go look deeper into the hardware. So basically the hardware is our printed circuit board that has all the sensors and our microcontroller that talks to them all on board on our small board that we have.
Then we have our firmware, which is the code running on our device that handles all the reads and writes from the sensors, and then it packetizes the data and sends it on over USB to our software.
Yeah, and then finally we have our software, which would be running on board your UAV, and this would be performing state estimation as well as unpacking the data, and in this case, visualization, so you can see the actual state estimate and how it corresponds to real life.
So let's dive deeper. We're going to start off with the hardware. We're going to go over our block diagram, the circuit board itself, and kind of some challenges we face with that, and then also the functionality of each sensor and our motivations behind picking those. So let's start off with our block diagram. Here we see at the top, this part is our printed circuit board. You can see all our different sensors, the different communication protocols they use into our microcontroller, and all that is going out using USB 2.0 out of a JSC connection, which is converted to a USB-A cable. And then using that USB-A cable, you would plug it into any ROS capable device. Today during our demo, we're going to be using a Jetson Nano to run a sim, but hypothetically, you can plug it into a drone that runs ROS, and we'll get more into that later. So then here's a picture of our actual circuit board. So we got a lot going on here, so let's kind of dive deeper into it. Here we have pointed out all our different sensors. We have our barometer up here, our IMU or initial measurement unit right there, magnetometer right down here at the bottom right, airspeed sensor right here at the top in blue, and then on the back side of the PCB sits the GPS. And then also finally bringing it all together is our microcontroller right here, connecting all of them and taking in all that data from all these sensors.
So now to get more into the specifics of what we have on board. So first I'd like to introduce a microcontroller, which is the main method for solving the task at hand. In order to packetize and sort of coordinate all these sensors, we have a microcontroller on board. This one in particular is very attractive because it has these communication interfaces that allow us to avoid contention when trying to access these different sensors. Additionally, it has hardware on board to help us offload the computation for reading these sensors to allow us to do things like average sensor data and other things on board the firmware. We can also have on board the USB hardware to be able to actually send things over USB. It requires its own protocol. So this microcontroller has it inside and all within this 10 by 10 millimeter package, and not too expensive. It was a great choice for our project. And moving past the microcontroller and into the sensors on board, we'll start off with the inertial measurement unit. This in particular has an accelerometer and gyroscope inside. This accelerometer and gyroscope is essential for doing state estimation on a drone, as it allows us to better understand our orientation and even position, since we get linear acceleration and angular velocity from the two sensors on board. This one we access over SPI protocol, which is just a communication interface of how we actually talk to it. In particular, it's kind of small and relatively cheap, and again, was a great choice for a budget.
Next, we got the magnetometer. So what a magnetometer does, for those of you who don't know, is it gives magnetic field strength readings relative to the magnetic field of the Earth. So sort of like a digital compass, you think about it that way, but in 3 dimensions. So it's very useful at providing orientation information, which is obviously useful in the drone. It's good to know which way you're going. Our particular one, actually, we ran into some unfortunate sourcing and manufacturing issues, as you can see right here. The actual sensor is pretty small, but we had to use this giant breakout board because we couldn't get this part in stock from our manufacturer, and it's pretty impractical to solder something like this at home. But you know, sourcing constraints aside, this magnetometer is overall a very good choice. It's pretty accurate, it's pretty quick, and it's pretty small.
Yeah, so moving on to our airspeed sensor. So this is actually a differential pressure sensor that we then use to find airspeed using Bernoulli's equation. So we communicate with the sensor over I2C protocol, and it outputs 14-bit differential pressure reading and an 11-bit temperature reading. So 2 things kind of leap out at you immediately when seeing the sensor. The first is the size. It is 24.7 millimeters by 16.8 millimeters. Unfortunately, like all airspeed sensors are this is kind of the minimum size you can achieve because of the nature of the differential pressure that you're reading. You have to have this little kind of pocket of air, and you can't really get much smaller than that. And the second thing that leaps out at you is the price. At $72, that is not a cheap sensor. However, when it comes to differential pressure sensors, again, this is kind of the lower end. The only cheaper sensor we were able to find was $50, and that one was kind of sensitive to some humidity changes. So we figured we might as well risk it.
And moving on to the parameter, this sensor measures altitude, and how it does this is it measures temperature and pressure readings, and from this we're able to plug it into a formula and calculate altitude. So this sensor, specifically the TPS 310, it can use I2C or SPI. For our case, it is I2C, and the temperature and pressure readings are 24-bit data output for each one. You can also see how accurate it is at 0.06 hectopascals as well as 0.5 degrees Celsius. And as mentioned earlier, our goal for this project was mainly try to keep it as cheap and small as possible. So looking at how small this sensor actually is and the price just under $3 was a perfect fit for us.
Yeah, and here next we finish rounded out with the GPS. All you directionally challenged people, you probably used one of these to get here. Now, obviously we all know that GPS outputs a longitude and latitude of our current position. Specifically, what kind of makes this different than all the other sensors is that if you've been paying attention, this one uses a UART protocol. None of the other sensors actually were UART capable when communicating with our microcontroller, so this allowed us to use that to free up some space and not crowd all the other buses, I2C or SPI buses, and leave those for the other sensors. That was really nice. This particular model is accurate within 2.5 meters. And challenge we faced was kind of a similar story with the magnetometer. There was manufacturing limitations where we could not get certain GPSs that we did want, but we were able to use this breakout one, which obviously we're compromising with the sizing a bit, and so we also were able to put it on the back though to kind of save our space on the top of the PCB, allowing us to on the back, kind of helped out. Coming in around with $11, kind of the second most expensive sensor after the airspeed sensor, but still a decent price.
So now we'll start to talk about the firmware that makes all of those sensors work and talk the microcontroller successfully. So this here is our packet header fields. We packetize the data all into one big bundle, and it controls all the fields at once. There's a device ID here, which if you have multiple devices on the same COM port for some reason, you can pick out our device in the packet header. And then these sale bits right here indicate whether or not the data indicated is fresh as of like the last time a packet was sent out. A 1 means that it has been updated, a 0 means it hasn't. This is what the actual packet looks like. Each of these is a floating point number. So like magnetometer has 3 floats, X, Y, and Z. IMU has 6 floats, X, Y, and Z for accelerometer and gyroscope. And it sort of goes on like that. The total packet comes in at 72 bytes, so it's pretty small. And there's also a timestamp attached, which we forgot in the diagram. And this is our software flow diagram. This is how the whole thing works. Over here, you can see our interrupt service routines. So all of these sensors, with the exception of two, generate data-ready signals, which are picked up by these interrupt service routines. They are sent out over the main loop to indicate that there is new data ready to be read. The magnetometer and the barometer were actually reading some registers on them because we don't have the wires hooked up. And these registers just indicate that there's new data available. So we're in the main loop. If an ISR is detected that there is data ready, the handler will trigger and it will perform a read and send it on over to the packet. The packet gets a timestamp attached to it and it's sent out at a rate of 100 hertz or 100 times a second. And it's sent on over our COM port to our software.
And looking more into our software, we're going to talk about what ROS is, how we're using it, as well as state estimation, and our visualization. So what is ROS? ROS stands for Robot Operating System, and this is kind of where it gets confusing. Although it has operating system in the name, it's not an operating system. Instead, it's a set of software frameworks that are used for robot development, and it's just a bunch of open source libraries and pre-built packages that just the community has put together for robot functionality. So this includes controlling the robot, perception, simulation, state estimation, anything you can think of. And how are we using ROS? So for our example, as we mentioned earlier, we have our data packet that goes through USB and reaches a ROS capable device. So for us, we decided to use the Jetson Nano. And from here, we have ROS published data for each sensor as its own topic. So in the picture below, you can see we have our publisher node, and one topic will be IMU data all the way through magnetometer data, and you get the gist. Basically, each sensor gets its own topic. And then from here on out, we have subscriber nodes that subscribe to these topics and pull out the data, and then this data is then used for our visualization setup as well as our state estimation. And then we can get a more virtual example of the drone moving as we're moving our device. And for state and state estimation, Mark can explain a bit more about that.
Yeah, so before we get into state estimation, we should probably talk about state a little bit. Conventionally, state is position and orientation, as well as first and second order derivatives. So acceleration of velocity, linear and angular. And to process this state or provide an estimation of the state, we're using an algorithm called an extended Kalman filter. There are lots of algorithms, but we chose this one specifically because the way it handles nonlinearity on input. Yeah, so I think the two most important components of this algorithm would probably be our state prediction matrix or state prediction function and our prediction covariance matrix. And you can view this algorithm kind of as like a generalized least squares regression, where the objective function we're seeking to minimize is the trace of our prediction covariance matrix. I.e., we're kind of trying to minimize the sum of the residuals of our predicted state. So this algorithm works in two phases: predict and update. So during prediction, we use our previously estimated state as well as our most recent sensor data to generate a prediction of where we currently are in time at any point query. And then update, which is triggered by new sensor data, is performed where we then generate a new prediction of state and compare that to our previous prediction. And then we use that difference to adjust our state prediction function and our prediction covariance matrices accordingly. You may be wondering how such an algorithm maintains its accuracy over long distances, and this kind of how it does that is through use of like low variance sensors, such as like GPS or LiDAR sensors. And these sensors with low variance almost serve as like a ground truth. So like over time, your covariance may vary, but as soon as you get like a new GPS update, it'll shrink again. So going into how we use ROS, we have three nodes. We have our local robot localization node, or our local EKF node, our global EKF node, and our NavSat transform node. So our local Kalman filter node basically takes in IMU and magnetometer data and provides a local estimation of our state. Our NavSat transform node takes in our GPS and our barometric data to provide like a global estimation. And then our global node merges these two estimations of state and provides a global estimation of state, which is relatively, consistent throughout measuring it. It is prone to some discrete jumps due to the fact that you're using a GPS, which can't really update as smoothly as a IMU or a magnetometer. but it tends to hold up pretty well over long distances. And in addition to this, we're also using the RViz library, which is this visualization library pre-built in for ROS to perform the visualization of our state estimation. And I think we have a demo video.
Or not. Or maybe not.
Should just be able to click through.
As a low-profile, low-cost sensor package designed to provide all sensor data and generate a state estimate a drone would need to fly. Is intended to be able to plug it in via USB into any drone and provide sensory information. Here we see the printed circuit board, the sensor stick, that holds all the sensors being used. The board is just under 3 inches in length and about 1.5 inches in width, or for other reference, here's a banana for scale. Here we have a sensor stick, and through the JST connections, it is wired to a USB-A using USB 2.0 protocol. We have it connected to a Jetson Nano, which will receive the package data and generate a state estimate using ROS. Now we will show a visualization of the sensor stick that would sit within a drone, and you can see the simulated drone moving with the sensor stick, changing its roll, pitch, and yaw.
Yeah, so that reaches the end of our presentation. We'd just like to give some quick thank yous, especially to the Capstone staff, Dr. Yoka, Jimmy, and Alex. You know, we couldn't have gotten this done without you guys, as well as our former TA Venkat. And then all the lovely folks at AirVironment, specifically Phil and Tiziana, who are here today. Thank you so much for coming out to support us and also helping us out with our project along the way. I don't know if we have time for questions.
Any questions?
All right. Yeah, what's up?
If you guys wanted to make another one of these, like how hard would it be? Would to produce another like
So basically we have all the PCB files and the BOM with it. So as long as given, obviously we mentioned before we had manufacturing concerns where not all the sensors were in stock. So obviously that could always still be a concern. We all know those issues with ordering parts, but it's pretty easy. We just upload the files. We use JLC to produce the PCB. You just send them all the files and then also the BOM list of materials and we have all the part items they would want. And then it would come around to like roughly 150-ish per board, right?
That's with them being a prototyping kind of manufacturer. So in general, you probably do it in bulk and it come out cheaper.
Yeah.
Maybe.
Yeah, so since it's going to be using the drone, is it over constrained selection of the microcontroller and the sensors?
Yeah, so we picked a lot of low power sensor applications or sensors with low power loads, and they're all running in their low power form. So just like minimal current draw.
And then through the USB, the whole board's powered as well.
Were you able to test or gather a log of data running around with this thing under real world conditions, or was it mostly just across and up?
Yeah, so we couldn't actually go too far because our USB cable wasn't very long, so we kind of limited to a tabletop. But it would definitely be interesting to like put it on a real drone and just collect logs or something.
But just following up on that, the data that you did collect was in a small distance. Are there certain sensors that I don't know? You have a lot of packets there. It's very impressive. Were you able to see that you had reasonable data from all of the sensors, or are there some of them that
Yeah, definitely. But
are an open question? Is there ground truth with that data?
I think it's definitely important to like the selection of sensors that we have is very important because depending on any one sensor for an estimation of state it just doesn't work out. I think like we had an original version that just used the gyroscope for orientation and it was all kinds of wonky. Yeah, I think kind of there's some components that looking back, we should maybe prioritize more, like getting a really nice IMU, although it's expensive, drastically reduces the amount of work you have to do when you come to like tuning your Kalman filter and trying to actually provide these state estimates. Because I know like our IMU, it experiences like a little bit of like gyroscopic bias and like or drift and like accelerometer bias. So having to account for that is kind of tricky when it comes to the state estimation.
And then that particular demo, like I think what you meant was like some of the sensors weren't as used as heavily in that particular part as other, like the airspeed, we're not getting much airspeed readings at that for like in the video, I'd say, if that's what you want.
Did you test that?
Yeah, we had blown on it, yes, absolutely. Yeah.
The tuning and so, yeah, I mean, I think, yes, a lot of this, you had to learn a lot to like with the components, but yeah, how much tuning was involved?
Honestly, a considerable amount, but I feel like there's definitely a lot more to be done as well. I think, I don't know, it's kind of a complicated concept, and it just requires like a lot of time, especially like when you look at you need the variances of all your sensors initially, and you would like to trust the data sheet, but then sometimes the data sheet just isn't correct. Like, I guess they're just like manufacturing errors. Like the library also doesn't really account for gyroscopic drift and accelerometer bias. So what you have to do is you just have to set the covariance for the affected components like a little bit higher, so it trusts those readings less. But yeah, in terms of that, I think it's definitely we did like an okay job. There was maybe like a week or so tuning, but definitely I think there could be some more work done on that. Yeah.
Good job, guys.
Yeah, thank you.
Which is about
Do these both work? All right. Good morning. Thank you all for coming. We are Viewpoint, and we are bringing to you a vision for the future. But before we do that, let's introduce ourselves.
Yeah, so I'm Tim. I'm Omkar. I'm Nathan.
I'm Krizika.
And I'm Ryan. So, what are we trying to solve? Tim, you want to tell us?
That's a good question, Ryan. The problem we want to solve today is the lack of accuracy and precision that comes with eye surgery that eye surgeons must use. For example, we have vitreoretinal cataract surgery, which involves making an incision in your eye and replacing the bad lens for an artificial new lens. And in a surgery like that, we require a lot of delicate maneuvers, and something like accuracy and precision is very important. For example, we have latency. Any sort of latency or time delay that's involved in eye surgery is very important because it can really affect the performance of an eye surgeon, and it can affect how they make the decisions. Image quality is also very important because with something like an eye, we have to see a clear image of the image. Also, the depth image perception of an eye is very important. Ergonomics is also very important because the posture of an eye surgeon and how comfortable they are working under an eye surgery is also very important. So we have a video that kind of shows like what an eye surgeon might see for a video. So content warning right here.
There will be a quiz. You will be expected to do this during the live demo, so everybody pay very close attention.
Yeah, so this kind of just shows you the surgery that I told you guys about. This is where you remove the lens. And then here we replace it with a new lens right here. Overview. So currently we have, there's a currently existing system provided by Ingenuity that sort of already addresses this problem. So pretty much what's going on is there's a microscope attached to a stereo camera, which provides you with a 3D image that's monitored on a 3D monitor. But the problem is the image processing that is done on this system is done through a separate host computer. And that takes time because it's done on a separate computer via USB protocol. And our aim today is to cut the latency by doing the image processing real time on an FPGA.
All right, so before we get into that, just a quick overview of how stereoscopic 3D works. If you guys have ever been to like a 3D movie, this is just that. So you don 3D glasses, the monitor will kind of polarize the light so that only the left image can go through the left lens of the glasses. Only the right image will go through the right lens of the glasses. So we start with kind of these two like full-size 1920 by 1080 images of one from the left camera, one from the right camera. These images are virtually identical. There's just a slight difference to account for the spacing between your eyes. The difference is called parallax. It's kind of a random piece of trivia. And from there, there's several different, I guess, formats that 3D monitors will use to arrange this so that you can see it in 3D. But the two most common are top, bottom, and row interleaves. So the way that we achieve this is by kind of, as you can see, taking every other row of pixels from the left image, as well as every other row of pixels from the right image. And then if we want to see this again, we kind of stack in top, bottom, we stack all of the left above all of the right ones. And in row interleave, we just interleave them. So we have left, right, left, right, left, right. And at this point, if you were to just plug in our system to a regular 2D monitor and look at what you would see, depending on the mode setting, you would see either top bottom where the image looks kind of squished like that, or you would see this kind of blurred row interleave thing that just basically looks like if you were to take off your 3D glasses in a movie. We do also support a third format, column interleave, which is kind of, as you can imagine, like row interleaving, but with columns. It would just been a lot of extra work to animate. So that's why we don't have it up here. But this is what VP3D does. The rest of the work is done by the actual 3D monitor. So if you imagine in this next animation that red represents kind of the left eye polarization and blue represents the right eye polarization, we kind of have something, looks like it skipped a little bit. We kind of have something like this. So the top bottom of the TV will actually stretch the two images and overlay them, whereas in row interleave, it doesn't actually have to apply any sort of image transformation. It just polarizes every other row of pixels because the image is already formatted in that correct way.
All right, now that we know how to get a 3D image, let's take a look at what sort of parts we need to get that done. So we start with two camera sensors rather than just one. Having two lets us create a better stereoscopic image. These two cameras feed into a custom adapter PCB board that lets us connect these two cameras to an FPGA board. We're using the Polar Fire FPGA board. It comes with a bunch of GPIO buttons on it, two of which have been configured to trigger interrupts. One of them allows us to select between all of the 3D modes that we support, and the other one lets us switch between the left and right polarity of the two cameras. Finally, the FPGA board connects to a 3D monitor via HDMI. A little more about the FPGA we're using. As the name might suggest, this FPGA is designed specifically for high performance image processing and rendering, which makes it perfect for this project. It comes with a single soft core RISC-V 32-bit CPU, has a bunch of reprogrammable GPIO buttons. It supports the MIPI, CSI2, DSI, and CS interfaces for visual data transfer. And it comes with HDMI 2.0 and 1.4 ports on the board itself.
All right, so we have our high-level system design right here. So we'll start off with the specialized hardware Verilog IP cores. This is pretty much responsible for creating an image frame and how like different image bits and pixels are packed together from different memory addresses. We also have the C code that's run by the RISC-V CPU on the FPGA. And this is pretty much responsible for the configuration of peripherals and communication protocols, the different peripherals like the button and the sensors and things like that. And yeah.
All right, so that's it for hardware. It's going to get into software now. Software. So we didn't start from nothing. As a basis, we use video kit demo code for microsemi, which supply part of the board parts. What this demo code does is very useful. It does all the image processing for us initially. So it takes analog data from both image sensors from the image board, converts it to binary data on the FPGA board. It buffers that in the DRAM, eventually reads it from the DRAM, does some processing on it in the video pipelining process, and then it overlays it into picture-in-picture mode, which is like where a smaller image bounces around in a larger image, kind of like that DVD logo that you see every so often. And finally, it outputs to the HDMI output.
Now, this whole process is great. It does all the initial camera processing for us. It does all the necessary initialization at first. But the main issue is this part right here, the picture-in-picture mode. Because what we want to do is we want to take these two input images and put them into a 3D mode, which is different than this picture-in-picture mode. So this area right here is what we need to modify. But before we were able to do that, we had a few challenges going into this. First and foremost, when we started looking into the code base, we were very unfamiliar with it. And it was surprisingly difficult to really understand it and really to jump right in and start coding and all that. A lot of modules had documentation, but a lot more did not. So we really had to understand from context what was happening, where it was happening, and what behavior was occurring. We also had difficulty confirming where image data was buffered and how many pixels are being processed at any given time. This was important because we need to know exactly where to modify the image in the code. And if we don't know exactly where to do that, or if we mess up timings, then we could really alter the output image and just result in a bunch of noise and not get anything. So this was especially important. Finally, the development tool we were using, and I guess the fact that we were just flashing on an FPGA board in general, compilation or a build time were pretty long, about 30 minutes or so every time we wanted to make some changes to the logic. So this reduced efficiency a little bit, but we were able to get over it in the long run. And the result is our final 3D mode implementation. So in this, the first thing we did was we created a whole new submodule. After all that, not understanding the code and having to look through everything, we finally understood exactly where to put it. And it was after the video pipelining process, right before the HDMI output. At this point, it takes in both input images, and then it uses logic to determine which pixel from which image will be relayed to the output image. So using this logic, we decide, okay, we want the left image first and then the right image, and this all is dependent on timing. So at this point in time, we want the left image, at this point, the right image, and so on. And this is the basis to implement all 3D modes. It's enough to implement row and column interleave, because it's just changing which pixel every so often using a counter. But it's not enough to implement top, bottom, and side by side, because the difference with those is that it takes both input images and then it shrinks them, it scales them by a factor of 2, and then puts them in their respective half of the output image. So we need to scale them. And the way we accomplished that was by modifying a bunch of memory addresses that we sent to the arbiter to retrieve image data. So when we retrieve the image data from memory, the addresses we make to the addresses we assign to take data from is what we change. And by changing how the memory addresses are created over time, we can successfully fix the scaling of each images, and as well as the position of each image in the output image. And finally, we also created several registers, which contain values that both affect the memory parts and the logic parts. So what these registers do, we use them for testing and to switch to final 3D modes. These registers contain values about, they tell the rest of the code how we want the memory addresses to be compiled, as well as which 3D mode we want to implement. And these are used with GPIO inputs to change the register values, which will be mentioned later.
All right, so one of the big challenges that we faced was the fact that by default, our sensors output at a 4K resolution, despite the fact that a lot of the closed source proprietary cores in this kind of demo code that's part of our video pipelining process that Nathan was just going over are only able to handle 1080p video. So what that meant was that as we were going through and actually reading these values out of memory, the process that Nathan just described, we would end up reading kind of a, like, if you imagine 1080p being half the pixels across and half the pixels up and down is 4K, you have effectively a quarter of the image size. And if you only read out a 1080p rectangle from, I'm gonna try to gesture with the microphone here. If you only read out a 1080p rectangle from a larger 4K, you end up cropping out this whole like 3/4 of your area, right? And so the problem with that is if you care about having precise spacing between two eyes on your sensor board, then cropping out a bunch of the image results in this really weird kind of dizzying like cross-eyed effect when you actually look at it through the 3D glasses. So to fix this, we implemented a very common downscaling technique called binning, in which we take essentially 4, for example, blue pixels from the 4K image and combine them into one blue pixel, throw that in a 1080p image, and then send that over to the rest of the pipelining process. Now, luckily for us, this is all done in analog circuitry that's built into the sensors. So it's very fast, very little overhead, and it's configurable completely on the fly via the kind of, I guess, FPGA MIPI interface that's exposed to the RISC-V over I2C, which is very simple to work with.
Now you'll notice that there are 4 pins here, but of course we're talking about RGB space, which is a 3-dimensional space. This is because we're actually correcting for the way that the human eye perceives color. So green is actually perceived a little bit differently, and we have to use what's called Bayer interpolation. It's a way that, taking the way that photosensors, image capture photosensors take RGB data, we then can convert it to this 3-dimensional RGB space, which we then use for our pipeline. But from there, we have to convert to what's called the YCBCR space. So in terms of the way that the human eye perceives luminosity, perceives brightness, it's actually not a linear function. And so gamma correction is the method in which we simulate that and then balance our videos accordingly. The last major concept that we utilized was alpha compositing or alpha blending. We were actually introduced to this in the demo code itself because of the way that picture-in-picture was implemented. Alpha blending is generally used as a way to create transparency effects, so it's essentially a very complicated interpolation. For us, when we're talking about creating modes like top-bottom, where we're experiencing a lot of data loss, skipping between rows, alpha blending is important for us to utilize there because we can go from a very downscaled image, and when we're pulling it back up, we don't create a very choppy image.
All right, so as we mentioned earlier, we're using 2 of the buttons on the board to implement mode switching and toggling between left and right polarity. So for example, if we say that we want the left image to be on top of our top bottom, or do we want the right image to be on top in top bottom format? And then we also support 3 different 3D formats that I mentioned previously. We have row interleave, column interleave, and the top bottom mode. So each of these buttons is connected to an internally wired GPIO block. They have the rising edge interrupt sent to one of the RISC-V's IRQ lines, and the interrupt handlers for each of these write to other internally wired GPIO blocks whose output registers drive the necessary signals to the video pipelining code that Nathan was talking about to actually propagate whatever changes we want to make onto the screen. And we store and remember all of this actual state, all of this setting in software. So it's very, very easy if we want to change like some little thing about, for example, just anything in the business logic. If we want to change, disable a button, if we want to say, like change the order that you cycle through 3D modes, if you want to add another 3D mode, that's all very easy to do. And we can flash it, go from like a mate clean to actually have it running on the board in about 30 seconds. So very, very convenient to change this stuff.
All right. So this is the design flow for the basic design flow for the entire final implementation. First things first, not shown here is the cameras are first initialized with the correct bidding technique, gain values, and timing, and so on. And then we go to the main loop for how the image data is processed and sent to the output monitor. So initially, this right here represents the flow of image data, this column here. First things first, we use the microsemi code to process some of the camera data, and all data is taken from both cameras, converted to binary, it's buffered in memory, it's later unpacked from memory, it's processed in the video pipelining aspect with Bayer interpolation, gamma correction, all that. And finally, this is over here is a module we implemented, which decides which pixel from each input image will be overlaid to the output image, and then finally it's outputted to the HDMI output port. Over here is the GPIO interrupts that we implemented. The mode switch button and the media mode selection button. Whenever it interrupts is executed, it's sent to the CPU and it writes to the 3D mode and mode switch select registers. And then it changes 2 things. First things first, it changes how which memories are accessed to fix the scaling and position of the images for top, bottom, side by side, and so on. And it also changes the logic in this module that selects between the different 3D modes. In this module, it selects whether it's alternating pixels, whether it's doing that for rows or for columns, and whether or not it's just simply showing the left image on one side, the right image on the other for top, bottom, and side by side. So this is the entire design flow for how image data flows through our product as well as the GPIO interrupts.
So once all that processing happens, I think this is it. Okay. Once all this processing happens, what we get is
Yeah,
row interface mode. This is something that doesn't require processing in terms of the monitor other than polarization. So we're actually switching between camera polarizations here. You can't really tell. But once we move into top bottom mode, which will happen in a second. So this is top bottom mode. This is what is pushed to the monitor. Like we mentioned, we're switching between camera polarizations here is a little easier to tell. When that is processed by the monitor, it looks a little something like this at the bottom. I'm switching between the glass lenses, the left and right lens. So as we move the time
It's like
cone,
the video is getting a little jittery.
you can see a little bit of a perspective shift. It's a little hard to do it justice in 2D, so we will actually have this at our table during the poster session. So come by and check it out. So now that we have all our parts, we have to make them look pretty. What we do is create a two-part 3D printed casing. The important things we were trying to focus on here was, like we mentioned earlier, we have this lens adapter that allows us to mount our individual image capture sensors, as well as interface with our actual microscopes. When we first acquired the adapter, it was set up for the OR microscopes that Alcon and Zeiss and all these other companies produce. We have since altered it to 50 like MS5, which is what we'll be using for demo today. The other things we tried to address were light bleed, because these are very, very small sensors with a very small field of interest with a lot of light that they're dealing with. So right here, we have our completely enclosed space so that none of the light from the FPGA anywhere else can actually reach the sensors, as well as an exposure toggle, which is on the adapter itself, kind of contracts and expands just like the human iris. So as far as the surgeon is concerned, all they're interacting with is magnification, focus, and any sort of lighting system that the microscope itself requires. So there's not really much of a learning curve in terms of using it. The other thing we tried to do was increase ventilation. We did break a board during winter quarter, and considering that these are about $1,000 each, we wanted to make sure we didn't do that again. So ventilation was something we also prioritized. The ports itself are all accessible. There are spaces for the buttons, as well as our 1080p, 4K, and for HDMI, and our power and flashing capabilities. This is what the final system looks like. We will also have this up for demo. So if you'd like to come around, play with the microscope, we'll have tweezers and all that nonsense. That will also be there. That concludes our presentation. We would like to, of course, give special thanks to our professor, Yoga, the TAs, Jimmy, Beckett, Alex, as well as our wonderful mentors at Alcon, Yupei, who couldn't be here today, and Hiro, who is.
I was in the back.
So thank you so much. I hope you enjoyed our presentation, and we'll take any questions.
Yoga, the mic's dead. Oh, there's bangers. Yeah, what's up?
So what were the latency gains by using that FPGA over a traditional computer?
So we actually haven't tested with. So we actually don't know the detailed specs of the current Ingenuity system that uses a USB. I don't know. Hiro's here. I don't know if you know. I don't want to put you on the spot. But we just know that USB typically has a several millisecond, like several tens of milliseconds of latency. But not only is there it just died again. Not only is there latency, there's also just the fact that, you need a huge gaming computer with a big like GPU to do all this video processing. Whereas when you're doing it on the FPGA, you can literally fit it on top of a tiny microscope, and it uses a lot less power as well. So there's kind of two parts to that.
What challenges were you guys being faced?
Oh my gosh, there were a lot. So first of all, none of us kind of going into this had a lot of experience doing FPGA development. I mean, I think we've written Verilog for, some classes, but nothing with FPGAs, nothing with VHDL, nothing with any of this like smart designs. I think Amkar and I have taken 153A, actually Professor Brew is here, I see. We took 153A, and that was really helpful with trying to hook up these GPIO interrupts that I was talking about, because we had to manually set all that up in kind of the soft-core RISC processor. It wasn't just like a matter of kind of enabling them from straight C code. And on top of that, we were also given a completely brand new, unfamiliar code base that did a bunch of video processing, which none of us knew anything about either going into this. So not only were we trying to learn the domain of video processing, we were also doing it using an FPGA, which is kind of brand new to most of us. And we were kind of just thrown into the deep end and said sink or swim, right? And the code was very minimally documented. Is this better? Very minimally documented, so it took us a while to kind of get oriented. And again, huge shout out to Hyro, who I keep calling out, but he was very helpful in kind of positioning us because he is an FPGA engineer at Alcon. And so he was able to kind of guide us in the right direction and actually implemented a preliminary version of the top bottom that we then built on and corrected and fixed some FOV issues and other kind of alignment things to actually produce the final product. But there were a lot of issues that I haven't even covered. I don't want to ramble, but there were a lot of other things too.
Did you ever look into whether you could find a 4K version of all this stuff?
We did not look into it super in depth because the documentation for this all says that it only supports 1080p and it's all straight from the microsemi vendor. So I guess we just assumed that since they said that in their documentation, it wasn't feasible, but no, we didn't look super in depth into whether or not we could find it.
We also did have conversations with the microsemi support team, and
We
there was
did, yeah.
clarification that we couldn't do 4K unless we went specifically with their design team. So that was a paid service, and of course,
Yeah,
being a
they
captive
basically
project.
said just pay us to do the project for you and we'll be happy to, but we didn't want to do that, so.
So it didn't appear to be a limitation of hardware, it was a matter of just.
No, I don't think it, like the hardware supports 4K and we're able to like, if we take the demo code and plug in a 4K monitor, then it will show one image. That was with the demo code. We haven't tried that with our code. But the actual processing that deals with handling 2 frames doesn't work with 4K. Yes.
Do you have any problems when you change the modes with the pipeline being bollocks, that you haven't clear it or having to synchronize the pipe when you do that?
I don't think so.
Not really.
Yeah, it was-
We initially encountered issues when we did it before the pipeline, but because
Yeah.
the pipeline is the last thing before it's outputted to the HDMI monitor. And if we did it before that, which I've tried doing several times, it just results in a bunch of weird coloration in the output image, or it just looks completely different from how you'd expect. Not exactly noise, but not exactly an image either. When we put the module after the video pipelining, like after all the pixels were processed, each pixel was processed, we were doing one at a time, and we could just take those pixels and just place them how we wanted, and there didn't seem to be an issue in regards to how the output image was. There was issues when we were doing the scaling, when we were modifying memories and how it was being read from memory, because that also messed up the video pipelining process a little bit. But the way we implemented it, well, it's fine now, I think.
Oh, so the data that you're getting from the image sensor, you mentioned, is it 4K data?
Yeah, so it comes in as 4K, and then what we do is we actually, and this took a little bit to figure out because again, documentation was very sparse. But the sensor is capable of doing this binning process that I described and kind of downsampling it to 1080. So we effectively just tell it to do the binning, but we had to configure a bunch of different timing parameters. We had to configure the layout of the binning, like you can do 2x2, 4x4, 3x2, whatever, like you can do whatever you want. So getting the right combination and then also getting it so that it properly fixed the like gain values of all the colors. Because as Krithika was saying, right, if you have 2 green pixels for every one and for every one red and blue, then you can't set equal gain values for all of them. And when you go through this downsampling process, it further messes it up. So it was a very, very extensive process of just trial and error to try and get something that looked not like too purple or too red or something.
What was the speed how many frames per second?
Do we know? I think it's 60 FPS. It's basically real. I mean, it looks real time when you look at it. We're not testing on a high refresh rate monitor, so we can't say that it can go higher than 60 because we've never tried, but I think it's just fixed at 60.
So the process of the downsampling and that process, that did not affect the frame per second.
No, it's downsampled as it comes out of the cameras.
What about that broken board? How did that happen?
If you want to go into details, basically what happened was we had left it on for a long time because we were kind of doing our development cycle, just flashing, testing, and it takes 2 minutes to flash it straight to the board, but actually synthesizing the whole HDL pipeline takes like half an hour. And we actually are using a brand new like Ryzen 9000 CPU to do all this, and it still takes forever. I think what broke the board though was as I was switching it on one time, I accidentally put my thumb on this little capacitor right by the switch, and I think that shorted it because it started like beeping, and I think I have a video of it on my phone. It was just like a and I told Yoga, I was like, is this normal? What do you think happened? And he was like, it looks like it's broken. So we brought it over to Alcon. They looked at it with like a heat gun, and it was like 200 degrees in this one tiny spot right by the power supply. So we were like, it's dead.
It was beeping and there's no audio output on this board. I don't know.
Yeah, it was really loud. It was audible. Like it was loud. It sounded like an actual like beeper. It was crazy. Yeah, and it's like $1,000 board, so that was just down the drain. Just done. Yeah.
Thank you.
Thank you. Oh wait.
Should I keep this on? I'll keep it on.
Real quick, I wanted to clarify, we're gonna have two demos set up. One of them will just have a looping 3D video, so you can just come by and throw on 3D glasses. The other one will actually be interactive if you guys want to interact with the microscope system.
Do you guys want to take electrons? Do you guys want to take a microphone? Testing? All right. Hi, we are pigs. And PIG stands for Personal Information Gathering System. I am Anshuman Dash. I am the project lead, and I mainly work with computer vision and high-level logic.
Hello guys, I'm Henry Hu. I mainly work for the mobile application development.
My name is Jiwen. I'm mainly responsible for the Raspberry Pi setup and interface.
I'm Ethan, design and implementation of different drone modes.
Hi, I'm Matthew, and I mainly work with hardware and RD Pilot. All right, so in a combat environment, information is key for success. Traditionally, people either need to risk their lives or manually control existing solutions. We aim to address these by proposing an autonomous solution, which is both easily controlled and can stream back information and video to the user seamlessly. And for this, our solution is PIGS. PIGS is a network of autonomous drones which is easily controlled by a user on a high level through a mobile application. The user can command the network and to do various different tasks all through a touch of a button while it streams back information and video to the mobile app seamlessly. The user can command the network into 4 main modes: Orbit, Explore, Bird's Eye, and Radar. In Orbit mode, the drones will revolve around the user while streaming back information. In Explore mode, the user can dispatch a drone to a target area where it then sweeps around and streams back video. In Bird's Eye mode, the drone takes an aerial vantage point where it then streams a panoramic view of the surroundings. And finally, in Radar mode, the network uses computer vision models to detect and relay detected objects to the mobile phone. And without further ado, here's our video. Oh, there it is. Sorry, that's not supposed to happen. That's not part of the video. Don't really know what's going on.
Maybe size is too large.
just for context, that's not supposed to happen in the video. We will be, this is on the Capstone website if you want to see it, and we also will be showing it when we are tabling.
And I'll introduce the block diagram of our design. On the left hand side, we have the cube orange as our flight controller. And on the right hand side, we have mobile phone as our user's controller, and laptop is our ground station. In the middle, we have a Raspberry Pi to communicate between the flight controller and the ground station. It basically serves as a link to communicate and does jobs like sending commands, articulate corrections, and streaming videos.
Well, in our design, we use like 2.5 GHz Wi-Fi as a network provider, since Wi-Fi is more compatible with multiple devices and has great performance in transmission videos between drones, laptop, and phone. And they are all connected to one router for data transmission. And for the communication flow, we have like two kinds of data to transfer. One is the text messages containing the telemetry and command, and the other one is the videos that's to be displayed on the phone. Like we separate it into two different communication flow because they have two separate requirements. The video must takes more bandwidth, while the telemetries need to be timely displayed, and also it need to be on time to trigger like possible failsafe and avoid collision. So we have such split, so we can use several different protocols for the. And for the drone control, we have such a state machine, like we split into like two big parts. The part on the left is basically when the drone is still on the ground. So when it receives timestamp, it will go to civilized state, which is ready for control. And the other part is a guided state, which the drone after takeoff is going to go on the air and able to switch between different flying modes. And here's where we implement them. And we have such split because we can trigger failsafe or landing modes whenever user feel unsafe. And also it will be easier for us to do it with one-click user-friendly control from the Android app.
Alright, so here's our hardware block diagram. And there are three main groups of hardware. The first is all of these parts outside the box, which are all located on the drone. These are all the parts necessary to control the drone, gather sensor information, and communicate with the ground. And then we have these parts in this box that are located on the asset. These are all the things necessary to communicate with the drone and also interface with the user. And then this last group was used for the development of our project. It's a remote controller that was used to take manual control of the drone if necessary. So our choice of a flight processor was the Cube Orange. We chose this because it had the sensors necessary to gather all the data we needed to find the pitch, yaw, roll, velocity, and acceleration of the drone. And we also chose this as it supports RD-Pilot, which was our choice of autopilot software. And then in order for this project to work, we needed to know the positions of the drone. So we chose the HERE-3 GNSS, which gives us the latitude and longitude of the drone. And another reason we chose this was because it was compatible with the HERE Plus RTK base, which allows us to use real-time kinematic positioning, which increases the accuracy of the drone's location by using a moving base station that is located on the asset. And then we use the FrSky Taranis X9D Plus as our failsafe controller. This allowed us to take manual control of the drone. This was useful in our development process as it allowed us to first test our drones manually to ensure they were ready for autonomous flights. And when doing autonomous flights, we always had this ready in case something went wrong. We could quickly take control of it and ensure we were safe. And then we paired that with the FrSky Taranis X8R, which was located on the drone and connect it to the transmitter.
Yeah, and as mentioned above, we have Raspberry Pi to communicate with the ground. And we chose Raspberry Pi 3A Plus because it has a very powerful quad-core CPU. And in our design, we have 3 threads that must be running at the same time. One thread is to stream the video, and one thread is to report the flight information, and one thread is to encode and decode commands and send RTK corrections. And this Raspberry Pi just fits our demand for multi-threading. And it also supports for wireless connections, and that's why we chose it. And here is the Raspberry Pi camera. It is just a very cheap, compatible, and lightweighted camera that can provide a stable video to the mobile app.
And these are just all the other drone parts that were necessary to make the drone fly.
Okay, so let's go to the technical decision. You guys may notice that we use lots of very professional parts besides the traditional parts we know, because we consider that will have a better performance. Such as here, we use the RTK base station to get the location for the drone instead of traditional GPS, because we noticed that the RTK has both advantages in refresh rate and accuracy. So for our multi-drone system, the RTK will work better. And then for the network design, instead of using only one protocols, we've totally used four different protocols for the whole communication based on our requirement. Such as, for example, when drone sending commands to the laptop, because the drone is a very low performance machine, so we use the UDP protocol, which doesn't need to build up the handshake between 2 devices. However, for the laptop to phone communication, which sending the video to the user, we need to ensure the high quality videos sent back to the user. So instead of UDP, we use an HTTP based video servers, which laptop build up multiple websites, and the phone can visit the web page for the video. For the phone to laptop command and log, because the laptop will hold for the core of the communication and information exchange. So we want to ensure that it can be reliable. So instead of UDP, we'll use TCP protocol here. And finally, for the laptop to drone command, which laptop finally send user's command to the drone, besides UDP protocol, we also have a file sharing system that we will share file into the drones, which can ensure the drone receive all the correct commands when the Wi-Fi environment is not very stable. Then this is the command format we choose that share information between drone and phone. In this way, they share the information of acknowledgement, drone information, drone latitude, longitude, and also user information. In this way, user can quickly see all the information on their phone. So let's then go to the detail of our mobile app design. So this is our mobile phone design, which is the Android application. We integrate everything into one page, which user can access all the function easily. On the top of the application, this is a very large map. Now it's the map of the UCSB, but it also supports any corner of the world using the Google Map API. And here, user can not only interact with the map, it can also see the drone location, zoom in, zoom out, and set the destination of the drone where user wants the drone to go. And the second one, below the large map, is the camera, which the user can see the video sent from the drone, and it also can implement the object detection function, which you can see it draw the red bounding box on all the objects it detects. And the user can switch the video of different drone using those buttons before. And at the bottom, it is the list of command, which including takeoff, fall mode, and landing, and other safety mode. So the user can just control both drones with one click on those buttons, which is very convenient and straightforward. Then let's go to our final results.
In our final product, we have 4 modes. The first mode is orbit mode. It simply tells 2 drones to orbit around the asset given configurable height and radius. And the users can simply control the drones through the mobile app. And the video is also available on the app as well. Moreover, the drones can automatically adjust their positions based on the location of the mobile phone. And with few clicks, the user can make 2 drones take off and orbit around them.
And the second mode is explore mode, where where the user can select area to explore on the phone, and then one drone will dispatch automatically. It will choose a drone based on the closest distance, and it will arrive the area and swap around with to record the footage. And with one click on the phone, the drone will directly go back to the orbit mode without any collision.
In bird's eye mode, a drone is dispatched to an aerial vantage point of configurable height. From there, it sweeps its yaw around, getting a panoramic sweep of the surrounding areas, which streams back to the phone, and after, with the touch of a button, it'll seamlessly go back into orbit mode.
Finally, we have the radar mode, which we integrate the artificial intelligence-based object detection. In this mode, the drone will orbit itself and send a 360-degree footage back to the phone. And then our phone, the application integrates a YOLO V5-based object detection lightweight model, which it can detect all the objects, including person, cars, and other like umbrella or something else in the mobile phone, and then draw the bounding box which showed the user which object it detects. Besides that, after it detects object, it can also send the commands and information back to the drone to tell it to stay here to get more information. So this is the view from our mobile application camera, which you can see not only the video from the drone, but also all the objective and its confidence from the model.
The constraints that we put on ourselves made this project very ambitious. We would not have been able to do this without the help that we received. So specifically, we want to thank our sponsor, AeroVironment, specifically Phil and Tiziano, for their years of experience and their invaluable mentorship. We also want to thank Professor Yoga and our TAs, Alex, Venkat, and also Jimmy, for their overall support throughout the project, making sure this was a seamless learning experience. Without all of their support, we would not be able to get to where we are today. So sincerely, thank you. Yep.
So could you, I'm just curious, what will happen if one of the links between, either the phone or the laptop and the drone or the browser, what if one of those fails?
So the big thing.
Yeah, I think like in the commands, like it will have every time in the command it will follow a timestamp showing what time it is. Like we have a failsafe for the lost connection. If it haven't received new incoming command for a while, which means the connection is down, it will let itself. Yeah.
Yep.
For object detection, what model, what is the computer vision?
So we originally experimented with a lot of different things. We wanted to also try to implement our own models. But the big issue is we ran into processing delays, and meaning we ran into processing limitations, meaning we weren't able to both stream back video and record it. So we only had a limited amount of data. With that, we kind of realized all the models we performed and tested, they weren't able to accurately classify to quality we would have wanted. So we ended up using YOLO V5. And Henry, do you want to talk about that?
YOLO V5 has a very light version which can be processed on the mobile phone, and we can just download its weights and its file data from the YOLO base and apply it on our Android application. So finally, the way is that just like the mobile phone receives the video and it applied to the model. The model calculates the bounding box and then show to the user. Yes, all on the mobile phone. Yeah.
Yep.
When you showed the image with the object detection, the bounding boxes have a ratio on them, or a decimal value.
Yep.
What are these values associated with?
These are the confidence intervals.
Yes.
Yep.
Yeah. So is there any kind of security on the Raspberry Pi? Let's say I could somehow connect to the router, right? Would I be able to send commands to the drone to help out a lockdown?
It's actually the phone sending the command. It's a phone sending command to the laptop, and the laptop will pass those commands to the Raspberry Pi.
So no one except the laptop can connect to the Raspberry Pi. There's someone just connect to the Raspberry Pi anyway.
We have a special format for the communication, and also right now it's only the laptop able to talk to the Pi. Yeah.
Yep.
For explore mode, did the Google API give you all the data you needed, or was there any difficulty you might have had with respect to getting it to go where you needed it to go, as compared to say equations to just set some sort of rotation radius.
So right now it's like we can choose a point, choose a pinpoint on the map, and it will the Google API will give you the telemetry GPS info, and it will kind of send back to the phone, send back to the drone to go to the area, and once it check it as right to decision, it will start to surf around the area.
Got it.
Yep.
Did you guys need to program the low-level flight logic like orbit or collision avoidance?
So actually about that. So when I was mentioning constraints that we put on ourselves, that was a big thing. There's two main kind of aspects. One from hardware, we could have gone with a DJI drone or an existing drone and saved us a lot of time and effort, but we decided to try to build it as much as we can from scratch. And then more to address your question from the software side, we tried to keep as much work as we could to ourselves. So other than manually controlling the motors and low-level ArduPilot, all of the modes are custom made by us, including all of the object avoidance, collision detection, fail safes, positioning. We even worked on velocity controls and stuff like that because we had a lot of windy conditions and we were having issues with the drones kind of staying in the positions we thought they should be. So all of this was handled through us, which was a big complexity. Yep.
Yeah, so for that control for these different modes, what are the sensors you're actually, using? Like, let's say they're circling, like there's GPS on your phone, there's GPS on the robot, there's cameras, like how much of that?
So,
yeah.
The big issue that we ran into, and we wanted to do more stuff, but processing was a big constraint. So we weren't able to really use the cameras for any kind of object detection, but we were able to basically consolidate all of the drone's locations into the laptop, and the laptop is kind of intelligently able to kind of give it instruction, for example, indicating fail safes and stuff like that, saying if the drones are getting too close. But the sensors we use the RTK to get a relative position, so we have a close kind of, because also the video doesn't demonstrate it, the user can move, and the drones will adjust to that. And so the RTK gives us that. But all the calculations and that stuff, usually we get, I think, a lot of the information from the cube and the positioning from the RTK.
So they're trying to circle about the location of the
Every time in the message and in the message that the phone sends in the command that the phone sends to the drone, it will include its own location. It has when it's calculated whatever the position is going to go, or in the velocity command, it will also have such offset on the difference on the movement of the phone that it will orbit around the user instead of fixed point.
Are you using Wi-Fi for the streaming channels from drones through the laptop?
Yes.
So, and then when you have multiple drones, so you basically stream multiple channels at the same time, or you choose which one?
We stream both. So both drones keep streaming the video to the laptop, and laptop use the HTTPS to build up online servers. It has become a server, a laptop-based server, and both of them keep sending the video, and drone and the phone, the user can choose to visit each of them, both of them or each of them.
So the phone can also see the both streaming at the same.
Not it came down, but it's not originally supported by our application. But if you open two app, you can see both of them simultaneously.
What is the connection between laptop and the phone? That's also Wi-Fi.
Yes, everything is on the 2.4 GHz Wi-Fi environment.
We have a router, and all of them connect to that. It's not actually connected to the internet.
Yeah.
How's the orbit created? Is it getting a new position command
we have two options. We have when the drone take off, it will receive the current location of the phone user at the center of the circle, and it will to calculate a trajectory. And after that, you can choose whatever velocity control or position based control every time. The two drone has two different index, so it will always synchronize state without any collision. So we kind of based on that.
So the center of the base station is not moving. Does it do the coordinate by itself, or is the base station giving it new?
It's giving its new position because in the ArduPilot in the orange cube, the runtime for each time when we query the telemetry is not as stable. So if we want to run a if we want to have a, for example, this control or this command loop take several times, it will sometimes we'll have some timeout because of some hardware issue. So to be safe, we let the laptop to tell which position to go next.
But just to follow up, like for that, yeah, so there's eventually going to be in orbit path if they start off, you know, depending where they start off, compared to
like
switch to that mode, yeah. How does it assign?
Like in the takeoff, it has like 2 index, which is like 180 degrees away.
Right, but how does it decide where?
So, are you talking about like
Yeah, yeah.
which kind of yaw? It
Yeah,
chooses
yeah.
basically the point that's closest to it, so the orbit is seamless.
Yeah, when its orbit, when its one drone goal is 4, it will always return to the same index, and the other drone will also return to the index corresponding to that, so it will always keep 180 degrees away.
We also do have some more nuanced logic so that it doesn't ever have, like we thought about it, where we have potentially a path where a drone wants to go back and it collides. We do have logic like that so that the drones are in a safe position where there's no.
Yeah, just wondering if there's like a graceful
Oh, yeah.
transition to get.
Yeah. For all the modes where we release it back, we do have logic, and we, especially since we have the limitation of we don't have like LiDAR or any kind of sensors that can directly detect objects, we have to be very vigilant with our software kind of programming. And so the logic we've kind of tested and rigorously kind of made sure that it doesn't collide back.
You don't try to make sure that they're at different heights when they.
We did consider about doing that.
The height is a big issue because we use the height measurement by the air pressure, but because it's pretty windy these days, so the air pressure doesn't give you a very accurate value. When it's trying to tell it's go to 5 meters, it may be like 3 meters high. So, yeah.
Also, changing the heights would kind of limit what we could do with the cameras and stuff like that, because we did have future plans that we wanted to work with this.
I was just thinking of the transition time.
Mhm.
Thanks. Great job.
Yeah. I'm gonna pass it as well. Hey. Hello, everyone. Is this on? No. Hello. Hi, everyone. We are the Somali team. My name is Ebony Warren.
Riley.
I'm Robert. I'm Ryan. I'm Sammy.
And today we're gonna show you the reason why we created Wally and some of the goals we set out in creating him for this. The key components that we use, so like what we kind of circled our creation around. We'll also show you a demo video, and then we'll finish up with some challenges we faced and how we overcame those.
So to briefly introduce what this bomb was, there's this organism called ostracods, order of crustaceans, kind of look like that. It's like a mollusk without that. And there are many species of these ostracods that emit blue lines in various spatial and temporal patterns as a way to do courtship. And it's kind of like this. It looks like this on water. Now it looks quite bright, but actually it is rather dim. These bioluminescent liquid that's spat out into the water. The timing, they do this during nighttime when there's no moon, so it's at the minimum light level. And usually it's done with certain light pulses that are spread out into the ocean.
Okay, so what does this have to do with our project? Well, the purpose of our project is to help out the UCSB Oakley Evolution Lab's research, and specifically their research investigating the evolutionary history of these bioluminescent courtship signaling in these ostracods. And so how will we achieve this? Well, oh, that's too much. So how will we achieve this? Basically, what we'll do is we'll capture, or our project will capture this footage of these courtship messages under the water using 2 cameras. Then later on, this video will be stereo rectified to create 3D models that change over time for further analysis. Additionally, we will also be acquiring the environmental DNA or the eDNA that just floats around under the water. And so we'll isolate the ostracod DNA, and then that will be used to provide further context for our models. So let's back up a bit. What even is SMALI? Well, SMALI stands for Stereovideographic and Macromolecular Acquisition of Low Light Emitters. And yeah, so to explain, stereovideographic acquisition is for the video with 2 cameras. The macromolecular part is for the eDNA home system, and low light emitters are our ostracods. And so essentially at its core, it is a submersible underwater camera system, and that will be deployed on the ocean floor. And in fact, later this summer, the Oakley Evolution Lab will produce more of these SMALIs and will actually deploy them out in the Caribbean for actual real research, on the field research. And finally, it is the improved version of WALL-E, its predecessor, and it was an old Capstone project, probably around in 2018. Now, what does WALL-E stand for? WALL-E obviously stands for Waterborne Autonomous Low Light Electrovideographic Videographic System. Yes. As you can see over here, this is what the old WALL-E used to look like. It's a little cute. It does resemble a Pixar character a little bit. But as you can see, this is our design. It's completely redesigned from the ground up. It's got lots of, it improves upon a lot of the limitations of the old WALL-E over here. It also is packed full of new and additional features. And as you can see, you can't really tell here, but it is a lot smaller. It is fairly smaller than the WALL-E itself. It's a smaller version of the WALL-E, SMALI. But yeah, let's look into what's changed.
Yeah, so one of the big things that we've been able to do is that we've quadrupled the runtime. So it went from 3 hours to 12 hours now. This allows researchers to get a full night cycle of what the ostracod mating signals are like over the course of a night. We've also created an automatic syncing pipeline so that they no longer have to manually sync the 2 video camera feeds. We've also added a new sensor to the module, so it's not just cameras now. Now it can also detect light levels in the water. And we've also added the eDNA collection system that will collect eDNA in our during recording. We've also improved the video quality, so we went from 480p to 1080. We've also compacted, so it's less. The previous WALL-E was a lot of air, and it was very hard to get to the bottom of the ocean floor. They had to use a lot of dive waves for that. We've packed it full of devices so that they no longer have to use as many dive waves, and so it's does more, it weighs more. And we've also fixed the camera. So this is important for stereo video rectification because the camera distances need to be set. In the previous WALL-E, there wasn't a way to permanently fix them. In our current WALL-E, we've created a device to permanently fix the 2 camera distances so that you only have to calibrate it once. And we've also made it cost and stable and stability. So basically what we've done is we wanted to make sure that researchers could create more of these SMALIs in the future. We've also made it modular so that they can decide what type of modules they want to add onto it for cost effectability. We also try to not have too many customizable parts so that they can purchase almost all of the parts on the open market in the future when we're not here to create it for them. So going over some of our key components. One of our key components is the brain of the system, the Jetson Nano. This is in charge of encoding and decoding our video feed, as well as auto-syncing the camera systems and managing the eDNA collection system. The reason we went with the Jetson Nano over another device is because of its easy to use, easy to interact with, and its stability just overall. This will allow researchers in the future, if they need to edit the code going forward, they'll be able to find resources online on how to do that. We've also went with Wadtech IP cameras, and so these cameras were picked for, again, their versatility. So they're also, we know they'll work with low light situations underwater, as well as research in the lab, so they're multifunctional, and it also records at 30 FPS. And we went with an SIPM module. So this is a silicon photomultiplier. They originally wanted a PMT, a photomultiplier tube. We decided to go with a silicon photomultiplier just because of the energy requirements, and we thought it would pair better with the Jetson Nano. And then finally, we have our Surfx filters, which are used in our eDNA collection system. The reason we went with these is because they've already been used and tested in the lab for this exact purpose, but now they're able to actually deploy this out on the field via our eDNA collection system. This is our block diagram. So again, a key thing that we went into this design is to make it modular. So we wanted researchers to have options. So we first started with our stereo camera system, that's the base design, but then we also added on a light intensity module as well as an eDNA collection system module. These two are not required for the system and can be, you can have it configured in different ways. So you can have just the camera system and the light sensor, just the camera system and the eDNA collection system, or just the camera system. And we'll go into details about that right now.
So focusing on our camera system, one of the largest accomplishments we have in our camera system is our camera synchronization. So we're able to use an open source piece of code called GStreamer pipeline software. It uses a simple sync option. It provides us with video audio pipelining and hardware accelerated encoding and decoding plugins. So we don't need any complicated code in order to handle our camera syncing. We can just use GStreamer and our Jetson Nano to accomplish this for us. We also have a camera preview mode. So when you're placing Smalley down on the bottom of the ocean floor, you want to know where to point it. So when you start up Smalley, it starts up in this camera preview mode, and it uses similar function to a recording, except it redirects the video pipelining sync from file sync to image sync. It displays the asynchronous footage, but it has a small delay, which is pretty minor. We also wanted to test fixing our camera disparities. So you can see on this picture on the left, it is a bit curved. I don't know if you can see this red line. It's not exactly straight. That's just due to inherent disparities within the camera. You can see we were able to correct this on the image on the right. You can see it's a lot straighter. So yeah, as I said, most cameras have inherent disparities. We want to remove these irregularities to allow for more accurate and efficient depth estimation.
So moving on to the pump system, this is for three main components that are controlled by the Jetson Nano, So it consists of four components: the electric valve solenoids here, which are useful to isolate a singular filter for sampling, when that's triggered. And also we have a filter itself, which retains the DNAs onto its membrane, given enough concentration, which is about 2 liters of water. And here's the pump system, which is basically the heart of the entire system. Water gets pulled in through here, go through the entire system, through here, through the filters, and then out again. And the flow sensor, which here helps us verify how much has been collected and ensure that we have enough water for a concentrated sample. Here's the water pipeline overview. Here we have the flow sensor where the water first goes through, and then the pump. And then either one of these is activated, a singular one is activated, and the one that is activated, say for example this one, all the water will go through here, through the filter, and then out through the ocean floor. So some quick specs on this. We have a 12-volt pump that is rated at 400 milliliters a minute. In reality, we get about 200 milliliters a minute because of the obstructions and the sampling filter. And so it takes about 10 minutes to collect a 2-liter concentrated sample. The software is configured to collect 3 samples at 10 intervals. And also we made it so that it's as replaceable tubing for research sterilization. Here's a quick graphic of how a first pump works. Just pushes the water with the rollers in and then out.
Okay, so this is the light intensity measurement system. So it's not necessarily stereovideography. However, the Oakley lab wanted to see, for lack of a better phrase, what the osteopaths themselves are seeing. So we wanted a high frequency intensity measurement system. And so right here we have the SIPM and ambient light intensity sensor. So there's 2 sensors. So this is the ambient light sensor, and this little square right here is the SIPM. So what SIPM is this is what is known as a SPAD, or a single photon avalanche diode. In other words, a single photon. The measurement is done with like single photon counts, or in photon counts is like the order of magnitude of the light that's measured. So this is far more sensitive than the ambient light sensor, which is what is known as a photodiode. So this one has a larger range of intensities, but lower precision, whereas this has a lower intensity range, but higher precision. And so this right here this is a 3D printed case. There's holes right here so that future groups or future Capstone teams can apply what we call optical filters, which can reduce the types of light that's coming in. We're only focused on blue visible light. That's the range, a very small range of the light frequency that's emitted by the organisms. So these are the dimensions of the sensors. Now, the SIPM data flow is that, well, first of all, before the SIPM actually measures data, we want to ensure that it can actually measure data. So what I mean by that is that the SIPM sensor is very sensitive to ambient light. So if there's too much light, it just shuts down. So we have an ambient light sensor, a second light sensor that can measure the overall room, not room, but ambient light intensity. And then it ensures it measures the ambient light, and it only allows the SIPM to run if it's at a some maximum threshold. So this ambient light sensor sends information to the computer, and then the computer will ensure that the SIPM runs during those allowed light levels. And finally, as I mentioned earlier, we want to measure what the ostracods are seeing. And what that means is what is known as retinal perception rate. So in literature, we know that the fastest perception rate, the fastest amount of images they can see per second is roughly 160 hertz. And so we ensure that this data that's being saved from the SIPM sends measures photocurrent. And that photocurrent is sampled by ADC, an analog digital converter. We have ensured that we have at least 200 samples per second that's saved to a CSV file. And that will be used in tandem with the stereovideography data to study ostracod light intensity patterns.
All right, so we'll now go into our demo video and showcase how to use Molly turn on the water and its switches, which controls the entire system. So here we have the power switch, which basically turns on the entire system. And once the entire system starts, it will automatically log in and run a script on login, and that will initialize the preview mode, which we'll shortly have here. So here we have the preview mode coming up shortly, right there. And in this state, it will just basically wait for another switch to toggle. And this will disable the preview mode and enable the recording. And during recording, it will record up to a set time that's set beforehand. And if for some whatever reason you want to shut off this recording early, there's also this great shut off the second switch on the bottom of the power switch, which will ensure that the final recording segment is saved correctly. So here, and during the recording, the display here is shut off. So here we're using the graceful shut off to stop the recording. And here we just go back to the main screen. Here's a simple buoyancy test that we did with some dive weights to see if Smalley could actually sink to the bottom. And here we did some simple underwater tests, camera tests, using the checkerboard just to do some stereo calibration. And here are both of our systems underwater. You can see the screens there, the cameras are here, and this is the pump system right here.
Moving on to challenges that we face. So every problem comes with its challenges, of course. So some of the largest ones we had were our camera syncing. So initially we wanted to try and find hardware synced cameras purely because they were more reliable, but we were not able to find, we tried many iterations of them. We were not able to find any hardware synced cameras that were sensitive enough for our needs. So we moved on to using IP cameras that we knew were sensitive enough and GStreamer on our Jetson Nano in order to software sync them. We also had some trouble with our light sensor. So as I mentioned before, our SAPM malfunctions when there's too much light. So we added a separate ambient light sensor to activate the SAPM when it is dark enough. We also had some trouble with our water pathway. So of course, the cases we're using are designed to keep water out of the system. So we needed to find a way to safely bring water through the system without causing any leaks. So we used some vacuum plugs and marine sealant in order to accomplish this. And we also had some problems with overheating. So we're using a Jetson Nano for all of our camera syncing and other needs, which creates a lot of heat. Same with our power supply. So we have a 22-volt battery that has to step down to 12 volts and 5 volts, which again produces a lot of heat. And in a coax system, it causes a lot of problems. So we use some fans and forced convection to dissipate the heat. Yeah, so that's our project. We want to say thank you to everyone who's helped us through this yoga, Alex, Todd, and Cheyenne, and everyone else. If you have any questions, please let us know. Yeah.
Yeah, following your very last bullet there, I was curious when I saw that fan running, how did you fight the out of the closed systems? Are the end caps metal?
Yeah, they're aluminum end caps, so we're able to get the hands to them, and we also have a aluminum strip that redirects the heat.
It just has to get the heat away from the components. That's just the main part, and it will go onto the enclosure and the caps. And all it's
Yeah.
That 12-hour figure that you mentioned at the beginning.
Yeah.
Is that like a measure or the theoretical?
So we've measured it without the fans. It should theoretically get 12 hours with the fans.
Theoretically, it should be 16, but we estimated on watch.
Yeah. Yeah, so it's theoretically more than 12, but yeah.
How deep is this supposed to go?
It's not that deep. Yeah.
Still quite deep.
Yeah.
Would there be like a recovery for video in case like something happens?
Yeah, so the camera will save video every 30 minutes. So even if we're not able to trigger the graceful shutoff, it should still be able to save footage every 30 minutes. So that should still be safe for purposes. Yeah.
Staying on the ocean floor, is there any concern of like sand being picked up and obscured?
Yeah, of course there always is. So it's up to the researchers to find a good spot. Again, this is a predecessor for Wally. They wasn't that big of a deal. Once you leave the area, the sand should settle. There shouldn't be any of the other. Yeah.
So these are going to have multiple of these.
Yes.
Basically, like there's a good wildlife cameras.
Yeah. So we are helping the team build a couple of them right now.
Yeah. Got to figure out those are located. And for the 3 samples, like they're just going to put it in and it will stay for 12 hours. Are there different collection units for each of these?
Yes. So each collection unit has its own timer level and will trigger at those.
Or do you use the same pump?
It's the peristaltic. It's the same pump. Yeah. So it's one individual pump, and the water valves are used to isolate the water.
Do you have a question?
Okay. The shield for the SIPM, I guess. So if it's too bright, it destroys the sensor. Do you have a problem? Or it just may take a while for it to sensitive.
So the SIPM sensor actually has a temperature sensor on the back. What it does is, if it takes in too much light, it will actually the electrical components that facilitate this avalanche or photon to current process, that whole area heats up, and then we have electronics connected to the SIPM that shuts it off. And so it shuts it off before the break. In other words, it shuts off, and then if you turn it back on, it will keep running.
Okay, I was wondering how you turn it off, that shield, or just flipping a switch to the plan.
Okay. What kind of ambient temperature did you reach inside the container? Oh, the ambient.
I think we actually measured that.
I don't think
We measured the Jetson's temperature.
Yeah, we measured the particularly the Jetson on the sensor, and it's about 40 C. Stabilizes around there.
What was the challenge they had to face with choosing to design the body, the model body of
So like the case?
compared to the predecessor? The reason why it was a little bit compared to the way it was designed.
Oh, okay, I answer that. So the predecessor, the case was custom built, and they built a square. However, there was too much air in it. So the next best thing was to find if there was any underwater robotics teams that already have designs that that we can ensure that it's optimized for underwater, and it just so happens to be cylindrical. That is basically the only reason. There's just not that many places that knows how to make deep, semi-deep water enclosures.
With transparent glass for the cameras.
So that leads to the other question, which is there's a lot of air left in the focus of the box, was quite visible.
Yeah.
As opposed to the other one.
Mhm.
Did you guys investigate doing things like silicone oil immersion?
Yes.
It takes the pressure off a lot, and you can just fill the whole case with it.
It's to immerse the inside of it.
On the inside,
Yeah, we did talk. Someone did in our sponsors did mention that something about that, but we didn't really investigate that. 'Cause we already are like so far into the development, so that was too much to rework.
Thank you.
Yeah, that's what's dead.
Yes, congratulations. The mics. And the mic's not working. Yeah, that's the other one that also. So yeah, you see my
All right, hello everyone. Welcome to our senior capstone presentation. We are Team Hand LED. Thank you all for coming. Let's get this presentation started. So, first things first. Has anyone seen Iron Man? Yeah, great movie, right? Anyone remember the scene where he's building a suit with all these 3D holograms? He's manipulating them and doing all of that. Well, currently nowadays we can do that, but on 2D screens. Can we make that better? Question, answer, yes. So, what we aim to do, our project, is to elevate the current 3D model visualization experience. We can do this and has many applications in different scenarios, such as education. We can plot mathematical functions. Also in industry, we can plot CAD models. We can do interior design. We do landscape. We are motivated to do this because we believe through accurate visualization, people can truly learn and share the information being displayed on a more intuitive and a deeper level of understanding. So what did we do? We built a 3D display system that I lovingly call the cube. The cube consists of main three parts. We have a mobile application, we have a 3D LED matrix display, and we have a smart glove. The mobile application is the part that is used to generate the plots and models that will be displayed in the cube. And the smart glove is what's going to be used to interact with the plot inside the cube using gesture recognition. It's about time we introduce ourselves. My name is Ryan Chow.
My name is Sasha.
My name is Eric.
My name is Christine.
And my name's Anna.
So in our system, we have our smart glove, which has 2 inertial measurement units, 1 distance sensor, and 2 force sensitive resistors.
connected to the microcontroller and the Bluetooth module. The smart glove is connected to the mobile application via Bluetooth, and the and the mobile application is connected to the LED cube via Bluetooth to the microcontroller. The microcontroller is connected through 4 tri-state buffers to our RGB LED matrix.
Okay, so I'm gonna start talking about our components. So we have 4,096 of these RGB LEDs that are individually addressable, since we have a 16 by 16 by 16 LED cube. And it has a data input, data output, and voltage and ground input versus the traditional RGB LEDs. To control the LED data lines and to also reduce the load off of the microcontroller, we're using this tri-state buffer to drive the LED matrix. We put the tri-state buffer on this PCB that we made, and it's used to open the inputs and outputs to the tri-state buffer. This is the microcontroller that we are using, and it's an STM32. We use one on the smart glove and then one on the LED cube. We designed 2 custom PCBs for this. This one is for the LED cube, and it's meant to receive the input and also drive the LED matrix. This is the custom PCB for the smart glove, and it's to read the glove sensors and also to determine our hand gestures. This is the Bluetooth module that we're using, and it's a development kit that we use for communication with the LED matrix and also with the smart glove. So now I'm gonna get into our smart glove sensors. First one being this inertial measurement unit, which we use to determine the rotation and the shift gestures. This is our distance sensor that we're using for the zoom in and zoom out gestures on the glove. And this is the force sensitive resistor, which is basically like a soft pad that is sensitive to pressure. And we're using it to serve as buttons on the smart glove to determine which hand gesture is being read. Now I'm going to talk about the LED cube construction. So this is a close-up of how the LEDs look like when on the cube and how they're like soldered in. And this is basically our whole system setup for the cube. On top, we have the LED matrix, which is encased by this acrylic covering for protection. And then underneath, we have this metal sheet that will mount the cube and also to act as a heat sink for the cube. And beneath, we have our power supplies and circuitry. And so dealing with 4,000 LEDs is a lot of manpower. So to help with sort of easing that process, we 3D printed a lot of jigs to help with the process, such as this LED bending jig, and then also this LED strip assembly jig. And also many components on our actual cube are also 3D printed, such as this power base. And this is the bottom of the LED matrix, which has the power supplies and also the circuits. And as you can see, many of our connections have been made using shielded wire to help prevent noise from getting into our data.
For the construction of our glove, we have the PCB on the back of the hand, and we have our Bluetooth module located on the back of the wrist, one IMU on the back of the hand, and another one on the back of the middle finger. One distance sensor on the side of the thumbs, and 2 force sensitive resistor on the side of the face.
So the software flow begins with the user. The user can input a mathematical function or choose from a preset model. Data is obtained from sensor readings, and this data is recognized to a gesture. This gesture is encoded into a packet and sent to the mobile application over Bluetooth. The mobile application receives this gesture, applies it onto a model, and formats this model, which is sent to the LED cube over Bluetooth. This data is then fed into our LED driver, which powers the LEDs.
Now I'm going to talk about the gesture logic. So this is the full state diagram. I'm going to break it down first. Everything starts in the idle state. And so once the zooming FSR is being pressed, it will go into a zooming state. Once the shifting button is pressed, it will go into the shifting state. And once both buttons pressed, it will go into a rotation state. The rotating gesture is determined based on the orbital angle of the IMU on the back of the hand. And so once the maximum degree of change exceeds 10 degrees, it will send out a gesture in rotating in that direction. And so we have 3 rotation directions available, which is roll, pitch, and yaw. The zooming gesture is determined based on the distance measured from the distance sensor. So as you can see on the right, it's going to be the distance between the thumb and the index finger. And so the initial distance is going to determine whether it's going to be a zoom in state or zoom out state, and the current distance will determine which state it's actually going to be in, and it will update the app with the gesture. The shifting gesture is determined based on both the orbital angle of both IMUs and the linear acceleration of the IMU on the finger. And then so it starts with a starting gesture, which is gesture 1 over here, and an ending gesture, gesture 2. So there are 6 gestures defined. And here we have up, down, left, right, and front and back. Each gesture has a bound on it, and all these gestures are defined with orbital angles of these IMUs. And the linear acceleration accumulated from moving from gesture 1 to gesture 2 is going to determine how drastic the movement should be.
To achieve wireless communication between the glove, the app, and the cube, we chose Bluetooth. We couldn't use off-the-shelf Bluetooth hardware to achieve the functionality required, so we implemented our own custom firmware. So the firmware can be thought of as a state machine. Bluetooth module begins advertising, the device can connect to it, they exchange various parameters, and input and output data can now be handled. And if the device disconnects, the process restarts. So we developed 2 firmwares, one for the glove and one for the cube. The firmware on the glove handles only transmitting data, and the firmware on the cube is a little bit more complex in that it can also transmit data, which is used for a handshake, as well as it can receive acknowledged data, and the data is acknowledged so that it limits data loss. So the main functionality of the mobile application is the map logic. The user can input a function. An algorithm will iterate through X and Y values within a given resolution. The root finding algorithm will evaluate those values at each X and Y, and these values are rounded to the nearest pixel. The mobile app also heavily processes this data. The users can choose a color scheme. They can choose between 16 colors, 15 colors, and 1 no color. And the user can control brightness as well as choose from various gradients. And this color is applied onto the model. And then this model is then mapped to be formatted for the LED matrix driver. And since we're using 16 colors, each LED can fit into half a byte, which allows us to compress the byte array 2 times. So to make sure the LED cube and the app are synchronized, we implemented a handshake. This is to make sure that the app is not sending data before the cube starts receiving, because that would mess up our DNA buffers. So the LED cube lets the app know it is ready to receive. The app lets the cube know it's ready to transmit. Now the cube can begin drawing. And asynchronously, the gov can send in gestures to the app. The app will compute and send the gestures to the cube, which will map and then draw the display.
Now I'm going to start talking about how the LED actually works within the matrix. So here's a simple diagram of how the LEDs are connected. And all VDD and ground are connected in parallel, all data ins and outs are connected in series. The signal data will flow in from the first LED and be passed on to the next one like a shift register. So for example, if I want these 3 LEDs to be blue, red, and green, this following signal has to be sent. I have to send a reset pulse, a mixture of zeros and ones, and end with another reset pulse. According to the data sheet, it's on the right over here. A reset pulse is a low pulse for roughly 50 microseconds, and zeros and 1 pulse are a pulse with modulated waves with different duty cycles. So this is implemented using timer channel with DMA transfer. So for this simple code over here, a DMA buffer like this should be used, which zeros are used to represent resets, and then different values are in the DMA buffer for the AR values for timer channels. So now I'm going to explain how the data coming from the app is used to control the LED matrix. So the data coming from the app is encoded in 16 preset colors. And then so these data will go through a color lookup table and be decoded into different data, and then be pre-allocated to buffers used for DMA transfer. We have 2 buffers right here for timing optimization. So DMA will take these buffers and send out the signal one channel after the other. Eventually we're gonna have 4 channels, and each channel has 256 LED data. So in total, we need 4 stages to complete the entire transfer. This entire process takes roughly 100 milliseconds. And so to control different stages, we use tri-state buffers. Each output channel is connected to 4 tri-state buffers, and then which means we have 16 tri-state buffers in total. So for this grid over here, this is a base plate of the cube. These 4 towers are lit up in the first stage, and then the second stage. And so after 4 stages, the entire cube is being addressed. So these tri-state buffer not only allows us to choose a tower to address, it also allows us to isolate the cube from the PCB so that we're not drawing current from the PCB, but instead from the wall socket. Now to the performance. This is a simple graph displaying how the delays work within the entire system. Everything marked in purple is a process that has substantial amount of delay. So it starts from here. The user will input a preset function or a user-defined equation from the UI. It will take TG to actually generate the matrix within the app. After that, the app will stall until it receives the gesture data. Once the gesture data is received, it takes some time to transfer, of course. It takes some time to transfer and then encode the data before sending it out to the LED matrix. It also takes some time to transfer over here. Once received, it will take time to decode and then eventually take 100 milliseconds to display the data. P total here, it represents the entire response time from the gesture to actually displaying it on the LED matrix. So from experimentation, we see that for a preset shape, it roughly takes 260 milliseconds to respond to any kind of gesture. For a user-defined equation, it still takes roughly 260 milliseconds to respond to rotation, but it can take in between 300 milliseconds to up to 1 second for a shifting or zooming gesture. This is because we have to recompute the entire matrix for that specific equation. And so now please enjoy our demo video of the final product.
Last but not least, we'd like to thank everyone who helped us along the way, our Professor Yoga, our TAs, our sponsors, our friends who helped assemble the cube. It's a lot of work. And our inspiration for building the cube, malt whiskey. We will now open the floor for
So you have 4,000 LEDs in the box. So how much was the heat actually generated inside the cube? Is it enclosed kind of
So while working on the cube, it's not that hot actually, and we can actually touch the lead and one yeah.
So if it's not running on full power, which we didn't configure it to run on full power, it doesn't actually get any warm. And then the heatsink actually works very, very well in dissipating all the heat out of the cube. So
On the lower side.
yeah, it's on the lower side, yeah.
How much current per LED do you carry?
So
In million, right?
so this is a so basically this is measured based on the full brightness. So this is for white. And then for each LED it takes roughly 53 milliamps on full power, which we didn't configure that. So we only do 50% brightness for full brightness. It's a hard limit. So it takes around 500 watts. So 100 amps. So yeah. It's kind of like a very high power computer or like a microwave. That's not hard. Yeah.
Oh, good.
Oh, okay, Kritika.
When you're doing your rotations, and of course you're gonna have certain cases where you have a full, I don't wanna call it fixed, a full LED, right? How do you address that? Are you just estimating where your edge is, or are you changing your brightness?
Yeah, it's an interpolation assessment.
I don't know if you've seen the YouTube channel Hacksmith, but they recently released a video a few weeks ago trying to make like an Iron Man desk where they want to rotate a 3D object using hand gestures and display it on a TV or something. Do you guys consider using like cameras for the gesture detection instead of using the smart glove? And what were your conclusions on that?
That was our initial sort of idea for detecting hand gestures, but then we eventually steered more towards the smart glove just because we are working with sensors and that's what we have been sort of learning about.
So if you were to use like image processing to actually recognize the gestures, it's sort of very limited to the location that you're like performing the task. If it's not indoor, like the lighting changes, it's gonna drastically affect the performance.
Part of it was just most of these projects clearly somebody else's idea, and the team gets sort of thrown onto it. Whose idea was this? Like, who was your?
Oh.
Okay, UCSB. So Eric was the one who proposed the idea for us, and we went through it. And the cat, this is Anna. Cat.
Like what sort of? Because I can imagine you could display a model of a 3D airplane, or there are a lot of things you could do. It looks like what you focused on for this demo was like a surface.
Yeah.
For example, with MATLAB, I don't know what you're using.
Yeah, you can. It's basically any equation you input, it'll just plot it out.
So any mathematical equation can be plotted, and then we also added a little functionality, STL files, 3D CAD models. We can convert that into something that can be ported into the.
Have time to try to do things like 3D.
Yeah, we have well, we outside. We have like a cityscape and interior design STL file I converted to put into the cube.
And debugging it. Sorry, just one more question. Did you have like a whole, what we're not seeing, like debugging this on a computer screen to visualize like how the glove is working, or you just go directly to controlling things on the computer?
So debugging the glove is mostly done in like the debugging feature of STM32. So because since everything is done in state diagram, so I can basically monitor the state to see whether it's working or not. And then without the debugging window, I can also, because I also configured the LED, so I can sort of look at the LED to know whether it's working or not.
Yeah, it's different than some other projects in terms of like plotting data and like how accurate all the sensors was, because it's more of a user kind of.
Yeah.
How do you guys deal with the interrupts and things? I noticed you did that one sequence where you were holding the two
Right.
The FSR.
And, you know, you're moving your hand almost to the music. I was curious how you dealt with the interrupts with the longer 250 to 350 or more millisecond sort of time delay. Did you stack them up, FIFO? Did you ignore everything that came in while you were executing?
So are you talking about the part receiving from the app?
So yeah, the part of the information coming from the smart phone before it's translated to what the LEDs execute on. Did you stack them up, or did you kind of just ignore everything until you were ready to receive a new command?
Okay, so yeah, since everything is sent out asynchronously, it's just sort of like sending out continuously. I did give a short delay before sending out the next gesture so that I wouldn't overload the buffer on the app side.
Yeah, the delay is mostly on the app side, like computation, especially for map functions, takes a while.
I was wondering the function that was typed in on the screen looked like it was a function of X and Y and Z. So the what are you doing?
It's not a four-dimensional display, so yeah.
Unless
I mean, it's just set for zero. So you basically like you set for zero. You just solve for this.
Oh, the minus Z at the end.
Yes. Yeah.
Yeah, it's a good question. Yes. It looked like a surface.
Thank you.
Right.
And
they want to use your own stuff.
Hello, everybody. We are Defect Detect, a low-cost quality control solution at the edge. So here's our team. My name is Ryan. I'm the project lead.
My name is Anthony Pella. I am working on data synthesis and software flow.
I'm Joshua K, and I work on machine learning.
My name is Li Mingting, and I worked on the camera and the touchscreen display.
I'm Shaunak, and I worked on the hardware design. So current anomaly detection systems on production lines are extremely specialized, and they use low-tech microcontrollers connected to peripherals like color sensors and distance sensors in order to detect defects. These microcontrollers or these systems aren't good enough, and they require people at the end of the production lines in order to ensure quality. And they require specialized engineering development for every new application. What we're proposing is replacing these systems with equal cost AI-powered microcontroller solutions that can detect defects with much higher accuracy.
So now for a brief system overview. In the beginning, we have a collection of unfiltered pinto beans along with defective objects, which are placed at the beginning of our conveyor belt. And for our case, we decided to use almonds and pistachios as our defects, but we have found that our system is also robust to other defects such as pebbles and colored pinto beans. And as the objects go down the conveyor belt, they'll get captured by our overhead camera, and these images will be passed to our custom CNN model, which will perform inference and detect defective objects, which will be marked for removal. And as the objects continue down the conveyor belt, they will come under our vacuum system, which actually removes these defects and allows the good objects to pass through. So now we would like to show a video showing our progress. So now going into our hardware block diagram. Here's our complete hardware block diagram where the main components are the MAX 78,000, our defect removal subsystem, and our conveyor belt subsystem. And we'll be diving into each of those in the next few slides.
Yeah, so the heart of our system is the MAX 78,000 Featherboard. This is like an evaluation board that brings out all the interfaces from the MAX 78,000. The MAX 78,000 processor has an ARM M series core on it, and this puts it in like the microcontroller segment. And the reason this is important is that this part can't be compared to processors like, edge AI processors from NVIDIA or Qualcomm that you're used to. It's an order of magnitude cheaper and it runs real time. The evaluation board also includes a OmniVision camera module with the VGA 640 by 480 resolution, so like a really crappy camera, as you'll see later. And we use this camera to stream frames into our CNN model, which is the special sauce on the board, at the CNN accelerator, and also to the LCD display that we connect to the board to view detections live. So the defect removal subsystem, that's custom designed and 3D printed. It's an array of servo controlled ball valves that spans the width of the conveyor belt. When a defective object is directly under one of the ball valves, it opens and the suction from the shop vac sucks it in into our bad object bin. Each one of these servos is controlled by a PWM driver chip that connects through I2C. And what this allows us to do is daisy chain these chips together so we can scale the system to n number of ball valve servos. We also have a connection with the conveyor belt. We use one of the PWM outputs from the microcontroller in order to control the conveyor belt speed. And then we've also connected an optical encoder to the drive shaft of the conveyor belt. And this gives us very accurate position on the conveyor belt and allows us to perfectly time the suction of the objects. So once we had all these systems working separately, we integrated them on the slick PCB. So as you can see here, we have on the bottom of this PCB, we put the MAX 78,000 board. It plugs into a socket and it looks down at the conveyor belt. On the top, we plug in the LCD display. And then the PCB handles all the power distribution, all the different components, and it also includes some circuitry that allows us to isolate the conveyor belt circuit from our main circuit, and so we can use that PWM output to control the conveyor belt speed. And then it also includes the circuitry to drive the servos with the PWM driver.
Next, we're going to talk about our embedded software flow consisting of 3 parts. In the first part, we capture an image and then we load it into our CNN memory where we run inference and extract bounding boxes around defective objects. We then use our mapping algorithm to determine which servo that object is likely to pass under and what the optimal encoder value will be at that time. We then enqueue these encoder positions at the corresponding servo channel in our array of queues. And then finally, we pull the head of each queue and compare it with the current encoder value. And any head that's less than the current encoder value is marked for opening.
So as the first step of the software flow, image capture is the part we spend a lot of time polishing. So the main challenge here is that our CNN model requires an input of 224 by 168 image. And if we use only one single image to cover the whole width of the conveyor belt, the image quality is just not good enough for the CNN to do the detection. Because all the objects looks like very small and there's no pretty much details getting preserved. And another challenge is that we can not do like multiple images processing on at the same time due to the limitations of the SRAM storage. So our board has a maximum of 128 kilobytes SRAM storage, and one single image already took about like 70 kilobytes. So we can only do like one image at one time. So in order to overcome those two challenges, we come up with the idea that instead of using only one image to cover the whole conveyor belt, we get a double width image from the camera. So here the witness is gonna be pulling in for 448. And then we'll just crop it in the middle so we can get like two parts. One controls the left part and one controls the right part. So during detection, we'll just alternate between these two frames to get the detection. So first, for example, if in the first frame, if we're using the left image, we'll be using the left image, and in the next frame, we'll be switching to the right image. So in that case, without introducing like more SRAM storage, we are being able to cover the whole conveyor belt and also give a better quality image for the CNN to do the detections.
So now transitioning into the machine learning development process, we first start the process by generating artificial data that we will cover more in the next slide. But after we get this data, we start the process of training, where the objective of training is to detect any defective objects in the image and treat any good objects, such as the pinto beam, as a background. And after we finish the training, we have to do a process called quantization, where the microcontroller has limited computational resources and memory, so we quantize the model to 8-bit, which reduces the computation and memory required for integrating the CNN into Max 7000. And lastly, we test the model in Max 70,000, and we keep repeating the process until we get a satisfiable result.
So as Josh talked about, we took a somewhat iterative approach to our model building. I'd say over the course of the project, we generated about 20 models. And something we realized early on was the sheer quantities of data needed to generate a model, which is in the range of around 30 to 40,000. It wouldn't be tenable to capture by hand and then hand annotate each one of those images if we wanted to train as many models as we wanted to. So we decided to generate synthetic data. For this, we used OpenCV, and our process was that we would capture about 100 images of each object we wanted, and then use contour detection to automatically crop out and do background removal around those objects. We would then composite them onto varying backgrounds. You can see we used conveyor belt images, but we also used other backgrounds, such as these kind of more noisy stripe-based ones, to increase the robustness of our model. We would composite them with varying transforms such as scale, rotation, and size, and then also apply blur. And we would do this at random amounts, and so the 30,000 images we generated all looked different, even though we were only drawing from around 100 base objects. This allowed for fast prototyping and model building, and it would allow us to create a new model in about 4 hours instead of the weeks that a traditional approach would take.
So going now more in depth for the CNN architecture, the model that we use is called TinySSD, which is a variant of single shot detection. And what single shot detection does is give it an input image to the neural network. We will do a single forward pass through the neural network and get an object's class and location. And what's good about TinySSD is it has smaller weight and it's a smaller model compared to the original single shot detection. And some key trait to this model is that we extract the low feature map and the high feature map and combine them in the class and the location to increase the model's accuracy.
So during the whole development, we faced a lot of different challenges. So the first one is the camera. It is really sensitive to the external light. So I remember during the winter quarters when we have the system like tuned and working perfectly in the morning. However, when the light condition changes, and when it goes to the afternoon, the system just not working. The model just cannot detect anything. And also, at first, our camera is only being able to cover about 3 frames per second, which is a very low rate for doing detection.
I think the removal system that you're going to see outside is like the third iteration. We we had a lot of problems with air leaking, with like objects getting stuck in the pipeline. So yeah, that was one of the big challenges.
As I alluded to earlier, the data collection and annotation, especially in the first quarter, was a big problem we faced. It takes about 3 seconds to capture an image and load it to the computer, and so before we even have to annotate them, it would take weeks to generate 30,000 images, which is what we used for our model training. We overcame this by creating synthetic images, as I talked about, but as you can see, our first approach was not very good, and we did have a little bit of a hard time making these images look realistic. As you can see, this is the real, sorry, can you go back?
Yeah.
This is the real camera image, and then, yeah, this is what they look like in our first attempt.
So in order to overcome those challenges, we made a lot of improvements to our systems. So in order to keep the camera from the influence of the external light, we built an enclosure like the image on the right side, and which have like the flashlight attached onto the top and the casting light onto the conveyor belt to create a very constant light condition for the cameras. And also in the software part, we also manually set the camera's gain and exposure time. So to make sure that each picture has the same gain and exposure. And also we managed to increase the frames per second from 3 to around 7 by enabling the camera slipping between the frames and also using the DMA to transferring the images to the display.
And on the training side, we originally started with like 50 epoch and like 200 real camera images, and that led to like mean average precision around 30%. But then we performed better when we did like 100 epoch with data set size of like 40,000 synthetic images. We got around mean average precision around 93%.
In order to improve our synthetic pipeline, we fine-tuned our compositing algorithm to remove noise. At first, we were doing just like a basic binary threshold, but we fine-tuned that to remove noise and get nicer edges, as well as lower our contrast. We also added a sparsity constraint so that the layout of images in our synthetic images would more closely map to what they look like in real life. Now, putting all of these improvements together, we created a highly accurate model that we believe is perfectly suited for industrial settings. And we have some results on the next slide. I think we're very excited to show you.
Yeah, so here are the results over the last few months. You can see a visual representation of how our model got better. So here are results in April. At this point, we already had most of our hardware and software in place, but we will be treating this as the base case, I guess, to see our improvements. As you can see, there's still defects that make it through to the end and pinto beans that get sucked up. So now going on to May, at this point, we had attached the enclosure that was mentioned in the previous slide, which helped to keep the lighting conditions stable. And we also fine-tuned the camera registers and improved our non-max suppression algorithm in order to take into account confidence over multiple frames. And at this point, you see our recall has gotten much higher, where almost no defects are making it to the end, but we are still getting a lot of false positives. So now moving on to the last month, June, you can see our results have drastically improved. And at this point, the major improvement that we made was improving our data synthesis pipeline to generate better images, and then we retrained our model using those images, and we were able to get a nearly perfect accuracy, as you can see. So now we would like to show another video. Given all of the context, you can see how our system operates.
It's much louder in real life.
It is much louder.
You'll hear it in about 30 minutes.
So yeah, and if you want to see more of this or try this out for yourself, please come visit us outside. And we would like to say a special thank you to Professor Yoga for his guidance, Afshin, who's actually here, who helped us a lot, and Brian, both from Analog Devices, for their mentorship, and Alex and Jimmy, our TAs. Thank you.
Questions?
I think you mentioned this is like something you want to inflate the industry, right?
I mean, that's the goal of the project.
How does that handle more dense things? Like I remember in the first slides you had where it was like filled with them.
We chose a vacuum removal system, but there's a lot of existing removal systems in industries such as compressed air that are better at removing denser objects. But we felt for the scope of this project, a vacuum would be a much cleaner solution. So all you have to do for denser objects is change the removal mechanism, not necessarily the core hardware and AI technology, which is what our project is really about.
Yeah, I think this is like a reference design. So like the removal systems already exist, but the detection, the defect detection is what makes this different.
Did you test your model with more dense things? Like how did it perform there?
We tried with stones. We trained a model on stones and it detected the stones, but just the vacuums wouldn't suck them up.
You mean like the sparsity of the objects, right?
They're all close together.
Yeah. I think it's we did. So there's two different models. There's the model in PyTorch that we test, and we have like a lot of success with that. But then once you quantize it, put it on the board, you get a lot of different results. So I think the model is definitely robust enough for that. But then there's more testing required when you actually quantize it and put it on the board.
From what I remember on the board, it can handle about 3 objects in any one frame. And these are very small frames because this is probably about a 3-inch slice of the conveyor belt and only half of it. So, it's only a couple square inches and it can handle inference on about 3 objects before you start getting inaccurate results. So that's it's a decently high rate.
Is this if they're like right next to each other or if they're spread out?
That's over the course of that's over the whole spatial domain of the image. One issue, it doesn't really have a problem when objects are close. One issue you'll run into is where you'll have a good object next to a bad object, and our servos, our vacuum channel only has so much resolution, and so even in our final images, you would have seen some pinto beans in there. Some of them were in there just because they had the bad luck of being next to an almond, and so they had to get removed.
Yeah. The training algorithms, since you chose a sensor setup with multiple sensor fields to regard, what happens when you have just partial objects or objects that come between the 2 sensors? I imagine that's a task with training algorithms.
There's overlap between the two. The way we do the cropping, there's overlap, so you'll never have an object that's like in half both frames. And then we also have, if you look at the other side, we have like multiple opportunities to there's multiple frames, right? Depending on the speed of the conveyor belt, you get multiple frames on target. So there'll always be one case where the object is fully in a frame.
Great. And then I know we're running late, but on the accuracy of your algorithm, when you say 93%, is this on synthetic data or is it real data? And does that mean false positives or, is this like how many out of 100 photos were 100% correctly identified? I was just kind of wondering what it meant.
So the 93%, I believe we gathered for our validation set, we did gather real images from the camera. The 93% is related to the precision, which I believe is the number of true positives over the total number of positives collected, which maps to basically how many pinto beans did you see in the final, like how many false positives did we have? And we had a pretty low false positive rate, especially after our final changes, and we had 100% recall rate, which means we detected 100% of the defective objects, which in an industrial setting for this is probably the most important stat to look at.
With how many did you how many images did you? I guess like real images are you?
Our validation set was about 100. But we also gathered real data on we would run it for maybe 100. Those pictures we gathered, we'd also get stats from that because that was a real world example of false positives and negatives for our system as a whole, not just our model.
Thanks.
Your original sensor had what resolution?
It's a VGA sensor, 640 by 480. But the way it works is since we can only store that resolution image, we read out all the data, but then we just throw away the stuff we don't want every frame.
And I assume things would work better if you were able to handle a much larger set of pixels at a time. Like if you had higher resolution, you'd be able to.
Yeah, if we had a more powerful microcontroller.
So would that have cost a lot more? This microcontroller is pretty inexpensive.
Yeah, I think it's really cheap, but Yeah, that's what I was gonna say. You can scale this, so like you could have like a little sliver of the conveyor belt for one, and you could have like 5 of them side by side, and it'll still be cheaper than using, something else.
But I think we're everyone runs. Right, so when you're running PyTorch, I presume you're running using just full data, right? Did you consider trying to do anything to reduce the data resolution in the training side?
We were using 168 by 224.
No, not resolution spatially, the number of resolution. We're going to quantize the data anyway. Then quantize the model. Right? So it stands to reason it would be better if you quantize the intermediate results in PyTorch.
Yeah, that was one of the issues so I think it was using float 32s and it was, when we did it, we turned into int 8s was where, we didn't have a testing method where we could, have the feedback be on the int 8s, which it would have been better.
Right, thank you.
We don't need to much. I'm sorry. First.
Hello, we're data driven. I'm Arjun.
I'm Brian.
I'm Nicholas.
I'm Brian. And I'm Ashton.
Now we're gonna go over the problem statement. So Carl already talked to us with colorful and creative icons such as the check engine and the battery warning light. Those are some examples of how the vehicles communicate with the driver about its overall performance and health. However, when there's a fleet of vehicles, the single stream of information is a bottleneck. The operator of each vehicle has the responsibility to gather the information, gather the data, organize it, and store it. And this obviously would become very time consuming due to how many vehicles there would be. And we will strive to develop these data analytical techniques through visualization tools for the user to see these patterns and threads to be able to solve these potential issues in the future.
And since we have problem loss in translation, we thought of this end-to-end vehicle data tracking system as our proposed solution. So first, we collect live data from the vehicle, and this data includes but are not limited to GPS locations, including latitude and longitude, speed, vehicle speed, engine speed, all sorts of temperatures and pressures. And secondly, we upload this collected data to the cloud, Amazon Web Services, which will be discussed later. And lastly, we provide this data to the user, where registered users can access this data through their mobile phone's web browser.
To showcase our implementation of this proposed solution, we have a couple of demo videos here. We start off with the installation of the actual tracker module. So first we must connect the OBD2 port, with the OBD2 cable into the OBD2 port on the bottom of your dash. And then you connect the other side of the cable into our tracker module. And then lastly, we have to connect 2 external antennas, one for LTE and one for GPS, and then we place the module onto the dash of our car.
And here's the app, our system's app, or web app overview. And here's the demo for front-end map screen interface. And we have 4 features. The first one is interactive map, where users can scroll around just like every other maps in the market. And the second one is live vehicle marker placement.
And the third one is select vehicle to monitor different types of parameters. And the last one is search vehicle parameters, where users can type in the keywords they want to look for. And here's another demo for data visualization interface. And in order to see the graph, users can first click on the data views in the left and select one or more vehicles and choose the date range that traveled. And lastly, select one of the vehicle parameters they want to look at. And it's important to keep in mind is that these parameters are dynamically available, meaning that the parameters supported by your vehicles will be all displayed here. And you can not only see one vehicle's data, you can also compare multiple vehicles' data at the same time. And here's an example of comparing Nicholas and Brian's vehicle travel speed in one graph. And let's move on to implementation details. So here's the overview of our system block diagram. Starting from the firmware to the backend, and finally to the front end. So first, location data. One of the most important vehicle parameters, GPS data, is embedded in a position velocity time frame that's periodically from the microcontroller's built-in GPS and LTE modem. And another thing to keep in mind is that in the initialization and fix stage, it takes about 80 seconds for the modem to get the fix. And in this stage, the modem needs to gather enough satellite signals as well as making those signals stabilize. And another time is the round trip time from the modem to the satellite and back to the modem is approximately 1 second. And here's the relevant components of what I just discussed in our block diagram. Yeah, now I'll explain how we extract data from the vehicle port. So OBD2 is also known as onboard diagnostics, and it's been a part of vehicles since 2008. So if you have a car that's 2008 or newer, you definitely have this port on your vehicle. And it's located right there underneath the dash. This one and in our two cars, it's located on the bottom left, but sometimes it can be on the other side as well. And the data includes the things that we saw in the video. So specifically, we're dealing with this part of the project. We're also using the NRF 9160, which uses Zephyr, which is an RTOS that's based on Linux. So it's really easy to use. All the peripherals that we use, including our CAN controller, our IMU, and the GNS, like all these things have drivers already built into the kernel itself. So all we have to do is enable it, set some configurations, and we basically have to write 0 driver code. So this is the process of how we upload data. We first compile all the data from our sensors, the vehicle data, GPS data, and accelerometer data. And then we put this all together into a single UV data graph that we marshal together. And finally, we upload it to the cloud. And this takes 30 seconds, which seems quite long. And that's primarily because we use a single modem in our device. The limitation here is that we can't do GPS fetching and also uploading at the same time. So we have to do time multiplexing, which means that we get the GPS, we wait for that to finish, and then we sleep it, and then we let the LTE start working. And that'll have to finish uploading before it can go back and begin the loop again. And so this is the process. We fetch the GPS data, we wait for that to finish, and then in the meantime, we can use all our other sensors, fetching vehicle data, fetching IMU data, and then we compile that all together. And once the GPS is done, we can finally upload. And now Arjun will explain the other side of the graph. So something to emphasize is that one goal that we were definitely trying to achieve with this project was to make the data as easily accessible as possible, which is why we're going through all the trouble of actually uploading the data over LTE to a cloud and processing it and serving it on a website. So this is that stage of the project. Once the data has been aggregated by the microcontroller and sent over LTE-M, It's received by one of our services running in an EC2 instance on Amazon. This is the UDP listener. It listens for the packets coming from each one of the trackers, and it unmarshals them and decodes them into a much more understandable format. So you may have saw from the other screen that the CAN data or the vehicle data was really just a byte string, but here we actually process it into the different units that make sense to us. And once the data is decoded, we save it into a database for future use. So at this point, we have completed the flow of extracting data from the vehicle and then actually uploading it to the cloud and saving it to the cloud for future use. And this is the relevant part of the block diagram. So like I mentioned, it starts with the data all accrued over here. Once we collect it from our various peripherals, we upload it over LTE-M, different from LTE, by the way. It's on a different frequency. And it is received by the UDP listener over here, and then it's saved on the relational database in the cloud. So the next step is once the data is actually available on the database, we want to serve it to the user. And we do this in two ways. We serve it both via an API and a web app. So for our API, we simply directly fetch data from the database and then serve it on a live endpoint that's accessible to anyone on there. And this endpoint serves this API serves various useful endpoints that if a user wanted to directly access the data without going to the web app and suppose interface it with a pre-existing data analysis tool like Apache Spark or Splunk or any of these really sophisticated tools that can set a data source as an external API. So this adds a level of flexibility and interoperability with data analysis systems that are already out there. But if that's not the case, our data is also accessible through our web app, which is also hosted on the internet as well. And just like how I mentioned, a third-party service could access our API, our own web app accesses data via our API. And the features that Patrick mentioned earlier about calculating it on a map and serving that live data on a sidebar for a vehicle that you're trying to track, historical data that you want to view over time, all of that is available through our API and visible through the web app. And this is the last relevant part of the block diagram where data starts at the relational database, is made available through our API, and our web app accesses it via those.
Now we're gonna be talking about for the web app live tracking. We are able to track the vehicles by having our front end retrieve the information from our API, and after every 30 seconds, our interactive map would update itself so that the user could see the new location of the vehicles. The user can also select the vehicles to see the parameters that it has, as well as they could search a specific parameter if they wanted to. For the data visualization, we wanted to implement the plots so that the user could see the trends and the patterns, so they could see the change of each parameter as the driver is driving the car, as well as the user can select multiple vehicles, as of like Nick's and Brian's car. You can also compare the data based on the trips.
Lastly, we have the design of the actual PCB of the tracker. So with the schematics, it's separated into three main areas: the microcontroller with its sensors, the power distribution, and then the connectivity. So these three parts together form this relevant part of the block diagram. And here we have highlighted some important components like the 9160 SoC with its two external RF antennas. And one thing to note that we don't have on here is we programmed this board using a JTAG connector rather than USB. And so here's our layout. It's a 4-layer PCB board with 131 components. And here are highlighted the major components on the board as well. And so here's the 3D rendering and our actual product. So some challenges that we went through. RF circuitry is very, very sensitive, as shown on the right here. We actually went through multiple iterations of our RF circuitry. We started off with some onboard antennas, but after further discussion with our sponsor team, the matching circuitry required would have been too hard to calculate. And so we pivoted to these two external antennas. We are also learning and applying best practices for PCB design on the fly, especially for RF, like the rounding of the traces is shown on the right, and some shielding ground vias that are necessary to prevent interference, as well as various other PCB design philosophies. We also had some dynamic requirements that we were trying to keep track, RF being one of them, and some components going in and out of stock, as well as some components requiring some manufacturing techniques that would have been too expensive for us to use. And yeah, so now we have our full demo.
So in this demo, I don't know if it went kind of quick, but the tracker sitting right there on the dash was connected to the car like shown in the demo earlier. And we have two cars set up in this demo. One is Nick's Honda on the left and Brian's Volkswagen on the right. And those are two tabs open with two instances of our web app. One tracking Brian's Volkswagen on the right and the left one tracking Nick's Honda on the left. And I think this is just a really cool demo all around just because it shows the full data path, data flow from data being collected from our systems on the vehicle and then wirelessly transmitted over LTE to be processed by our cloud services and then made available to an API and then made available to a web app that you can access on any web browser. The data itself is updated live on the side here. Every now and then you can see the vehicle travel speed change each time a new data is transmitted. Probably stuck at the stoplight right now. Yeah, and then the 2048. And yeah, this is really just an overview of I think that concludes the overview of our map functionality. So we learned a lot during this project, and to start off with, I think one thing that we really grew to appreciate was the modular design of our system. So over this project, we mentioned various services that are either in the cloud or our tracker firmware that's running in the car. Having these different modules made it really easy to develop independent parts of the project, or these different parts of the project independently. I don't know if you saw, but it was a bit of an Easter egg in the previous screen. One of the cars that was shown in the corner was called Debug, and that's because we were able to split this up into different parts. We could have each part simulated while we're developing each part. So, for example, when we're developing the API, we can simulate the UDP listener. When we're developing for the web app, we can have simulated cars in the API, and complete development for each one of these stages kind of as time went on instead of being blocked. Another thing is we learned a lot about a lot of layers of technology in this project, from web app development to dealing with backend infrastructures on the cloud to developing firmware on our PCB and designing the PCB that we use itself. And I think it's amazing that we got a PCB working in the first spin, considering how much extra additional complexity was added by the RF circuitry that Brian was mentioning earlier. Not only that, we have so many other peripherals that are involved in communicating to the vehicle and collecting, for example, IMU data, aggregating it, putting it to the cloud. Like this worked on the first try. I think that's pretty cool. So we were pretty lucky that it worked on the first try, but if it didn't work on the first try, we needed more test points because we didn't really have a way to test things if they didn't work. And additionally, of the test points that we did have, we didn't label them super well, so we kind of had to look at the schematic every time we were like trying to find a specific test point, like what does TP13 do, what does TP7 do? We weren't really sure. We only made one small mistake on the PCB, which was an incorrect resistor, but it wasn't such a big deal because we could just solder another resistor on top of it, and even with the incorrect resistor, the board would still work. It just wouldn't have as high a voltage as it should have. It was 3 volts instead of 5 volts. And then one of the boards that we did make had an issue with the UART where for some reason it wasn't printing, but we kind of just didn't investigate it because we had 5 other boards that we could use. And finally, as I mentioned in the firmware side, since we used a combined LTE and GNSS modem, the time resolution of how we send data was really limited. It takes 30 seconds. So if we were to use a separate LTE and GPS modem, the bottleneck would allow us to maybe upload data every second actually, because that's how long it takes to fetch data from the vehicle. That's how long it takes to fetch data from GPS. So we could upload very frequently and you would be able to see a much more smooth experience on the web app of the car moving live. And this last slide is really just a catch-all for all the other ideas that we've had during the year that we didn't really have time to implement. And the first thing that really we started thinking about was creative ways that we could use our API. So this API again is just an endpoint to all this aggregate data that we collected over really the entire course of from the first time that a tracker is plugged into a car all the way to when you access the data. All that data is accessible, whether it's historical or live, and it's very extensible. You can just keep adding endpoints. And one creative way that we think we could use as endpoint is to potentially interface it with something like a large language model, so that instead of manually making a request to an API via curl or Postman or something like that, you can make a natural language request. Like, I would like to see the temperature for this particular sensor on my car, the traveler's temperature over the course of the last week, because I don't know, something feels weird when I'm driving the car. And then it would return that data because the natural language models are able to process your request into the format of a HTTP request, which can be made to our API. So we thought that was a pretty cool idea that we would explore if we had more time as well. Yeah. We also primarily designed our whole project around like a single user idea, which means that we didn't really have a security model. So if we were to scale this project up, we would have to develop a security model to make sure there's no like, if you're accessing a specific vehicle's data, you have to be authorized to do so.
Another thing is to take remote control of the vehicle. I know Tesla has like this feature, but in the future maybe we can like take control of air conditioning or lock or unlock the car even if you're not like sitting in the car.
If we were to scale up this project as well to many more cars in the fleet, we would also have to create a distributed system for API endpoints. Currently, we have just one API instance running. If it goes down, then you have no data. So we would have to scale this up using a distributed system somehow.
We will also try to implement a interoperability with the vehicle systems, such as a dash cam, how we could use that to record the trip, and how possibly the user wanted to see the environment of where they were at to see if it changed the parameters as well. And lastly, we will want to thank you the UCSB CE department, Dr. Yoga, our TAs Alex and Jamie and Venkat, as well as the CACI for always helping us throughout the year. Thank you.
We can take in 5 seconds and
But like you talked about having an INU and it's running out of its own round. Like how are you, what are you using to make the car's speed? Is it the speedometer? Is it?
Yeah, so speed is actually directly fetched from the OBD port. So it's whatever the car thinks its speed is what we're fetching. The IMU turns out to be not too useful because it's a 30-second resolution, right? So you're not actually able to observe the data. You don't have enough data to actually use it for something useful. Like maybe you can see like he's accelerating way too fast at this moment, but that requires like the perfect timing. Like the IMU is recording exactly at the moment where he's accelerating too fast, and we're uploading at that exact moment.
Yeah, just where there's some blending of
Yeah. So you're right in that we do take various peripherals and then package it into the one datagram. So the data that appears on our front end is a mix of the various peripherals, including the CAN bus, the IMU, and the GPS. There's no distinction from the user perspective.
The car has an integrated GPS. Does that thing also appear the CAN bus?
I'm not too particularly sure. So the OBD port is specifically made for emission standards. So what we see like was like emissions related. I mean, California added like all the other things into the standard as well, like vehicle speed, like how hard you're pressing on the gas pedal, brake pedal, right? So you might be able to see GPS, and it's also manufacturer specific. Which we don't know what the proprietary standard is. You need like to spend a lot of money, maybe like $5,000 or more, to see like what they implemented on there.
So the way that Nicholas created the firmware, he's fetching all available PIDs from the car. So any data that's public, like that will respond to our request, will get brought back to us, and then that gets sent over and then processed later. So if it's available, on the CAN bus and it responds to our request, then yes, we will receive that data.
GPS basically.
Yeah. Yes.
Did you ever experiment with sending less data so it have a higher frequency?
Most of the bottleneck is not from the size of the data. The data packet is only like 380 bytes or something like that. The LTE-M was the modem was most of the bottleneck. The switching between GPS and LTE, because GPS needs to maintain a fix for it to get data quick. But we can't always maintain a fix because we're trying to use LTE at the same time. So if we were able to separate these two processes, it would have been a lot faster. I don't think it's about the size of the data necessarily. One thing we did think of was if we could have like a running list of like the last 30 seconds and send all of that at once. So while the website would only see the most recent, if we were using the data visualization, you would get all 30 seconds worth of data. So yeah.
Does the system get power from the OBD port?
Yes. So there's three separate ways we could power it. The OBD, the USB, and an external bench supply. But it works totally fine if you just plug it off onto the OBD. There's like a 12-volt line that we use.
Also, so like each of these components, while you're out and about, it doesn't actually like connect to some other Wi-Fi, right? It's all from itself.
Yeah.
How much does it cost per month to like be able to get that Wi-Fi?
How much was
So we're using a prepaid plan for our SIM card. It's like a $10 SIM card. I don't know how much data we used. I think over the course of the whole year, I probably only went through $10. So yeah, it's not that expensive. Data currently is in the order of like a couple hundred bytes.
300 bytes. Yeah.
300 bytes, yeah. So it's pretty efficient.